Shall we get started? Is it all good online? Okay. Okay, we've been talking about multiprocessors, but I have my lecture is also titled Multiprocessors. So we're gonna take a step back and give a different, broader treatment of multiprocessors now. But hopefully, so far you've seen an interesting collection of ideas and also problems in multiprocessing. These are some readings. I put Amdahl's paper as required. You'll read it, hopefully. How many people have already read Amdahl's seminal paper? No one? No one took DDCA here? I guess not. Okay. If you've taken DDCA, it was an extra credit. You would get 1% of the course grade for completing it, a review of it. Right? Yeah. Yeah, it's an important paper to read. And this is the full title, as you can see, Validity of the Single Processor Approach for Achieving Large-Scale Computing Capabilities. And we've discussed that. This is another paper that we will discuss, probably not today, given how fast we're going, probably next week. This is about sequential consistency. And there's another paper on cache coherence, the MESI cache coherence protocols, that is also here. These are some fundamental papers. There are a bunch more that we will discuss as we go along. But I want to give a broader overview of multiprocessing. And this starts with a taxonomy of computing in general. Basically, how do you design a computer is a question to ask. And this paper from Mike Flynn in 1966 classifies different computers based on how they operate. And there are two dimensions in which he looks at the problem. One is instructions and the other is data, right? You can have a single instruction or multiple instructions, and you can have single instruction, multiple data. Single data, multiple data. And then you have a 2x2 matrix. In this 2x2 matrix, one part is single instruction, single data processors. In this case, a single instruction operates on single data elements, right? A scalar. Another way of putting it is you have a single instruction operating on a scalar data elements. It's a scalar processor. It's good to think about it that way. Clearly, it's not necessarily a single data element, right? You may have multiple operands. Multiple operands doesn't mean that, doesn't violate this. Each of the operands that the instruction is operating on is a single piece of data. It's not specifying, each operand doesn't specify a million pieces of data, for example. It's just a single scalar piece of data. So this is essentially a single sequential thread as we know it today. SIMD is you still have a single instruction, but it operates on multiple data elements. Now, in this case, a single instruction specifies a lot of work. And there's a specific way of that work helps. Basically, you do the same operation on many data elements, right? This is essentially array processing or vector processing, as we have seen in DDCA. But you also have SIMD instructions in existing ISAs like x86, etc. But this is a way of designing the computer. You can combine these ways also. And we're going to briefly discuss that. So this is highly parallel, clearly, because a main benefit of single instruction, multiple data processors over single instruction, single data is clearly you unleash a lot of parallelism with a single instruction, right? It could be a million element vector. And we have discussed, again, if you haven't taken DDCA, I'd recommend watching the lecture on SIMD processors. Existing GPUs are SIMD processors today. We may have a lecture later on, but maybe not. Let's see, depending on how things go. Essentially, the benefit is you unleash a lot of work, but you also, a different way of looking at unleashing a lot of work with a single instruction is you reduce the overhead of control. Now, what does this mean? If you have single instruction, single data, every instruction specifies little amount of work. So the amount of control that each instruction goes through is a big part of the overhead, right? You're doing, really the computation is executing the computation on lots of data. But you need to fetch the instruction, you need to decode the instruction, you need to rename the instruction. That instruction needs to, a lot of processing needs to be done on that instruction so that you can do some work on two pieces of data. Right? That's a lot of overhead. If you look at the energy spent on an SISD processor, most of it is really spent on the overhead, not the computation itself. This is another way of thinking about it. I'm not even talking about memory over here. Forget about memory. This is just the computation that you try to do and what is required to enable that computation. It means to fetch the instruction, decode the instruction, etc. With SIMD, and this is one of the major benefits of GPUs, assuming, or vector processors in general, assuming you have the parallelism in your program, you fetch and decode the instruction only once, and you unleash 1 million operations, right? So the efficiency of this is much better. Essentially, the overhead of an instruction is really amortized over many data elements. Okay, and then there's a couple of other things on the other dimension, multiple instruction data. Now you have multiple instruction streams, I'd like to think of it that way, operate on a single data element. This is a bit of an awkward one. Essentially, the closest form is actually something that we have examined in the DCA also, a systolic array processor, which is a way of building machine learning accelerators today. Essentially, you input data to an array of processors, array of functional units. You can also think of it that way. And the data gets processed in one functional unit and transformed into data prime. And that gets input into the other functional unit. The other functional unit does something on it and then transformed into data prime prime. And then the other function unit gets it and transforms it and outputs it. So basically, the single data, I don't know what's going on there, some connectivity issue. Yeah. A single data element is input once to multiple instruction streams, if you think about it, multiple instructions in a systolic fashion. But it gets transformed in every operation. Right? I think this is the closest form that I could think of to MISD processors. And then there's MIMD, which is really the subject of what we're going to talk about today, which is you have multiple instruction streams operating on multiple data elements. Essentially, you can think of this as instruction streams that are separate from each other, and they're executing concurrently. It could be a multi-threaded processor. It could be a multiprocessor. And clearly, today's systems are a combination of almost all of these. You have MIMD processors in a multiprocessor, and each core in that multiprocessor is a SISD type of processor, which has SIMD extensions. And if you have an accelerator that is a machine learning accelerator, that may be MISD, right? A GPU is clearly a SIMD type of processor, but you can it also has some accelerators internally that may look MISD. Okay, so basically we use all of these paradigms today, which is good. So if you want to brush up on these different paradigms, we cover essentially all of them in DDCA, SISD, SIMD, MISD. Now we're going to talk about MIMD type of parallelism. But parallelism is more general, actually. Clearly, all of these processing types exploit parallelism in some way to improve things. Parallelism, in its very basic definition, it's really doing multiple things at a time, right? Everything can be parallel. It's not a function of just computers, clearly. Things from the perspective of computing could be instructions, operations, or tasks, right? And the question is, why do we do it? Why do we do it? Anybody? Why do we do things in parallel? Faster, exactly. Basically, the main or original goal is really improving performance, execution time, or task throughput, depending on how you define performance. And we're going to talk about Amdahl's law. We talked about it already. But that's not the only reason. There are other goals. Anybody? If you don't want faster, for example, you could want something else. And parallelism still can help you. Energy efficiency. Why? Mm-hmm. Mm-hmm. Yes, not maybe. It is more efficient, right? So basically, energy or power. You want to reduce power consumption, right? And if you have, let's say, n units at frequency f, for example, it consumes more power than 4n units at frequency f over 4. You can think about that. Am I right? I'm not right? Or do you have another reason to do parallelism? Huh? You can shut it down. Exactly. That's one way of thinking about it. But I mean, this may be slower, right? Maybe there's no time to shut it down. So the main reason over here is this is assuming you can perfectly parallelize your program, by the way. First of all, there's an assumption over here. You can perfectly parallelize your program, or you have completely independent things. That way you can, the baseline is you run n units at frequency f, or let's make n 1 unit at frequency f, and you have 4 units at frequency f over 4. Assume that they take the same time because you reduce the frequency by 4. This is still more power efficient. Why? Or maybe you can say this is not power efficient, then here's why. Why is 4n units at f over 4 more power efficient than n units at? Yeah, why? You could keep asking why forever, right? No, not physics. Well, of course it's physics, right? Yes. Yes. Okay, that's right. Okay, maybe I'll write the power equation, but I don't know how to deal with these things. Something is moving. So how do we? I should have used this one, maybe. Maybe we can. There should be a way of blinding this, right? Yes. Okay. Too much overhead, of course, switching, as you can see. Switching to a different medium always takes overhead. Yeah, basically, as you have said, the basic reason is at least dynamic power is equal to CV square F. Well, I guess I wrote large F. So if you reduce frequency, clearly this reduces, right? Now, if you reduce frequency, you can also reduce this because you don't need to really power your circuits as much with high voltage. And now this reduces. Now you have a quadratic effect, right? Or cubic effect. Once you reduce your frequency, the power reduces actually cubically. Make sense? Now, you could also argue, I didn't say that, I just looked at frequency, but assuming that you design a simpler core also, potentially you could also reduce capacitance. Who knows? Because there could be much less loading. A heavy out-of-order core is actually much harder to design than there are a lot of loading that happens on the buses, for example. A simpler in-order core, there's a lot less loading. So basically, you would definitely gain on this one, gain more on this one, and probably gain on this one. And your dynamic power is much lower, right? And this is dynamic. There's also static power. Even if you ignore static power, you gained already cubically, right? So if you actually have 4 n units at f over 4 and n units at f, you can do the calculation, right? This is clearly going to be lower power because again you get cubic reduction over here. Okay, I don't want to deal with that basically. 4 cube, let's say. Even though you increase the number of units by 4, you'll hopefully reduce the power by 64, right? Or 1664. Okay. But static power is also another thing to think about. And static power is usually related to temperature and area. Again, I don't have a good equation for this, but it's actually correlated with area, I will say. Because it's really leakage. If your area is larger, your leakage is also much larger. And if you actually design a smaller core, which was not what I said over there, it was frequency, but assume that you also design a small core, now you have lower leakage also overall. Actually, it's related to time also, how long you execute, but the time was hopefully the same. Right? Yes? Mm-hmm. Yeah. Yeah. That's right. That's why. Yeah, that's why I said, assuming you can perfectly parallelize things, I said you don't move data, right? Right? If you can perfectly parallelize a program, yeah. But once you actually become imperfect, meaning you have more data movements, you have more synchronization, you have some load imbalance, you have resource sharing, then of course your power savings will not be as much, right? In fact, sometimes you may increase the power, right? Because your performance will not increase. Make sense? Yeah. That's why that assumption is really important. Perfect parallelization. Okay, how do we go back? Should be a simple button, no? Oh, you need to share. Okay. Oh, I see. Okay. Okay. Oh no, my second thing is already there. Okay, I'll give it to you. So we've covered the power consumption and energy part. The second reason is improving cost efficiency, scalability, and reducing complexity. I kind of put all of them together, right? So if you have parallelism, again, assume perfect parallelization. It's harder to design a single unit that performs as well as n simpler units, right? If I have perfect parallelization, I'd rather go with n simpler units. Hopefully that's kind of obvious. I design a simpler thing and I basically replicate it a million times. That sounds good. So that was another goal. What about the third goal? Or if you have a fourth or fifth one? Yes? Okay. Okay. So you're saying performance and energy efficiency. Yeah. Mm-hmm. Yeah. Mm-hmm. Yes. Mm-hmm. Yeah, I agree, but that's not adding one more goal, right? You're actually covering all of them right now. They're simpler, which is true, power, better power, and also a better performance. Yes, I agree. But I'm looking for some other reason to do parallel computation. No other reason? There must be something because there's some space over there. It's not a trick question in that sense. We're going to fill that space. Why would you ever want to execute some thing on two different things? Yes? Exactly. I gave you too much hints, maybe. Basically, improve robustness, yes, dependability. Basically, if you have multiple of the thing, or multiple things, multiple processing units, you can actually do the same thing on both of those processing units and then compare the results, right? This redundant execution in space. I'm assuming no one else has another reason. That way I don't need to modify my slide because there's not enough space here, as you can see. Yeah, I'm joking. If you find some fundamental reason, we'll find a way of modifying the slide. Okay. Now, this is kind of like page limits in articles, right? They're designed to be like fixed, and they don't consider what's really important. We will add stuff to the slide, and slide will become bigger and longer. The article will become more. It's a fundamental to add something important, but the page limit goes against that fundamental thing, right? Okay. Yes. Yeah. Not necessarily linearly, but yes, certainly. Wait. Well, I don't want to talk about Dennard scaling, but that's not a bad question. I don't know if anybody can see this. Anyway, I don't want to switch too much. Okay, but basically, you can see it, right? CV square F. Essentially, Dennard scaling, which is a technology scaling, let's say, law that used to hold in the past. When you reduce the size of a circuit, it basically said that you could reduce the voltage associated with it. That's basically it. And it doesn't say anything about linearly, etc. In the original paper, there are some calculations, but it basically, you can reduce the voltage. But at some point, it became very difficult to reduce the voltage. So it's not happening anymore. So it's really related to the size of the circuit and how you can scale the voltage along with it. Clearly, there's a relationship between voltage and frequency, but I would say it's more complicated than just linear. Does that make sense? Okay, so it's an online question, so maybe they can write something. Okay. So there are different types of parallelism and different ways of exploiting them. We've covered some already. So instruction level parallelism, essentially different instructions within a stream can be executed in parallel. And we've covered a lot of these in digital design and computer architecture. Pipelining, out-of-order execution, speculative execution, VLIW, data flow. They're all exploiting instruction-level parallelism. Data parallelism, in this case, different pieces of data can be operated on in parallel. And SIMD is an example of it. Systolic arrays and streaming processors are also examples of it. And then there's task-level parallelism, in which different tasks or threads can be executed in parallel. This is actually really the multi-threading and multiprocessing, and we're going to look at that in detail. So what is task-level parallelism? So if you want task-level parallelism, you want tasks, clearly. And somebody needs to create those tasks. The more difficult problem is the first one. The easier problem is this one. You already have the tasks because they're different programs, processes, different jobs, for example. And you run them together on different processors. But let's take a look at the first one first. You want to partition a single problem into multiple related tasks or threads. You could do this explicitly using parallel programming. This is easy when tasks are natural in the problem. You can actually easily divide things into threads. This is difficult when natural task boundaries are unclear, actually. Loops, for example, could be parallelizable, but it's good to think about that. Or you could do this transparently or implicitly. This is also called thread level speculation, let's say. You can partition a single thread speculatively. Or non-speculatively also. I should probably add that. So a compiler can try to do this, for example, completely. A programmer can also try to do this. Well, sorry, not if a programmer does it, then it's not really done over here. But a hardware, I meant to say hardware. Hardware can actually do this transparently. So in a sense, if you could, for example, ship a part of the program to a large core transparently, you're really parallelizing things, right? Or a small core, maybe. Okay. Or you can run, so this is the hard part. We're going to talk more about this one. The easier part is especially when you have independent tasks that are already there. For example, you have different users, tasks from different users, tasks from different simulations, for example. You do the same simulation for 1 million different workloads, right? You're designing a processor and you want to simulate the different effects. So cloud computing workloads, for example, cloud computing systems take different workloads from different people. These have nothing to do with each other. Clearly, they're different tasks, and they could be executed on the same computer. They could be executed in parallel across different computers. Now, this doesn't improve the performance of a single task, of course, right? Which is the harder problem. So we're going to focus more on improving the performance of a single task in this lecture. Okay, let's talk about some fundamentals. There are two types of multiprocessors. They both exist today: loosely coupled versus tightly coupled. Loosely coupled, the main distinction between them is whether the multiprocessor, the different processors share a global memory address space or not. So in loosely coupled multiprocessors, there's no shared global memory address space. In tightly coupled, there's a shared global memory address space. Meaning when you run one program, it can reference an address that can also be referenced by some other program. Okay, that's interesting now. This is also called a multi-computer network, in a sense, network-based multiprocessor. So if you're all on the same network, they could also be thought of loosely coupled multiprocessors, and you can partition a program across my laptop and your laptop and your laptop and your laptop, for example. Right? These are actually loosely coupled multiprocessors right now. Maybe they're not explicitly designed that way, but they are. And I could actually partition my program across your laptops, assuming I have the permissions to do so, right? Yeah. Okay. So this is more traditional multiprocessing. So we're going to focus more on the tightly coupled part. It's also called symmetric multiprocessing. I don't like that name that much, but yeah, because what does symmetric mean? It assumes something, right? Essentially, existing multi-core processors or multi-thread processors are this way. Loosely coupled multiprocessors are usually programmed via message passing. You send messages, you send explicit calls, send and receive for communication. This doesn't have to be the case, but you could, because there could be programming is actually different from whether or not you have a global memory address space. But let me talk about this first, and then I'll clarify that. Essentially, you send explicit messages to data to communicate data between the processors, right? Because there's no other way, in a sense. Right? You cannot say load from location X. You could say that. There has to be some level software that translates that to messages. So that's the interesting thing about programming, right? Programming can be anything, and hardware can be anything. It all depends on what's in between. You could program a loosely coupled multiprocessor, assuming a global shared memory address space, assuming you have a virtualization layer, a software layer that translates what you have done to something that can actually execute on that hardware, right? Which is messages. So it's important to, I think, understand that. That's why I say usually. Of course, if you program this with a global memory address, assuming a global memory address space programming model, there's going to be some overhead to translate all of that to the underlying communication model, which is no global memory address space, right? Okay, so tightly coupled multiprocessors, a programming model is similar to uniprocessors, again in general, meaning you assume loads and stores, and different tasks communicate using loads and stores with each other. So you could think of it as a multitasking uniprocessor, except operations on shared data require synchronization. Right? Again, this is there's a difference between programming model and hardware execution model. You could have a tightly coupled multiprocessor, a multi-core processor, and you could program it using message passing. Right? This is a bit easier to achieve, I think, actually, than the other way around. Essentially, if you have message passing based programs, you just need to translate them to loads and stores. I believe it's easier. Okay, so I think in this slide, I covered different types of multiprocessors and also the distinction between programming model versus the hardware execution model. Right? Basically, the way these multiprocessors actually differ is really the hardware execution model, which is whether or not you have shared global memory address space to communicate or not. And usually they differ in programming model also, but not always. Okay, so there are many design issues. We're going to focus a lot on tightly coupled multiprocessors. There are many design issues over here. Shared memory synchronization, how to handle synchronization, what kind of synchronization primitives you have. We've already talked about some of these. If this was a more software-oriented course, you could actually talk a lot about, like parallel programming course. You could talk a lot about like how to optimize the locks, how to do better atomic operations, how to do better barriers, how to do better parallel programming. But we don't have time in this course for that, clearly. That's the subject of a full parallel programming course, which usually assumes shared memory synchronization also, actually, which usually assumes tightly coupled MP. But we're not going to talk about that. We're going to talk about some of the implications of it. Cache coherence becomes important. You need to ensure correct operation in the presence of private caches, keeping the same memory address cached. We're going to talk a lot about that next week. Memory consistency, ordering of all memory operations is important. What should the programmer expect that the hardware provides in terms of ordering? We're going to talk about that, probably not today, given that we're going slowly. We talked about shared resource management. That is actually an issue in, I think, all types of processors, but tightly coupled multiprocessors also suffer from that. And then we're going to talk about interconnects, which is also an issue across the board. But shared memory synchronization, cache coherence, and memory consistency are especially issues that are imposed by a shared memory model, especially hardware model. Now, if you do a programming model, shared memory programming model, I think you can run into some of these issues also, even if your hardware doesn't support shared memory, which is, it's not tightly coupled, but we're not going to look at that situation. Okay. So there are main programming issues. There are also programming issues. And we've covered some of these actually in tightly coupled multiprocessors. How to partition a single task into multiple tasks such that the load is balanced. I've given you an example from yesterday, right? Partitioning a book and counting the characters in a book. Even that task is not so easy in terms of load imbalance. Partitioning is easy. Load imbalance, getting the load imbalance right is not easy, right? Synchronization, how to synchronize efficiently between tasks, how to communicate between tasks. Again, we're going to cover the basics to enable better synchronization, but not talk about synchronization, how to do better synchronization in software better. We talked about actually mechanisms to enable this like in a fast way without making the programmer go crazy yesterday, right? Bottleneck acceleration, and today also. But there's more. If you are a programmer and if you want to optimize your program, you can actually do more. Contention avoidance and management, we'll talk about that. But there's also shared resource contention, we already talked. How do you maximize parallelism? And how do you ensure correct operation while optimizing for performance? That's actually interesting. And kind of what we covered yesterday, how we motivated asymmetric multicore was this, right? We don't want programmer to reduce the size of the critical section at the expense of correctness. And if you already have not so bad, let's say, critical section, we're going to accelerate it, right? Okay. So I will make an aside over here also, which is hardware-based multi-threading. Essentially, multi-threading is also another approach. It's not, basically, you can execute multiple threads concurrently, right? But these multiple threads don't need to execute on separate processors. They could execute on the same processor. In the same processor, there are different approaches to hardware-based multi-threading. One could be coarse-grained, fine-grained, and simultaneous. And again, all of these are implemented in today's processors, except processors that implement fine-grained multi-threading don't implement simultaneous and vice versa in general. But coarse-grained is over there. Coarse-grained means basically you have a single processor and you time multiplex multiple threads on it, multiple tasks on it. It could be based on quantums, time quantums, and that's what happens in today's systems, right? You switch to another thread after some milliseconds, and the operating system has a scheduler for that. Or you switch to another thread based on some event happening. This thread basically yields, for example. You can actually explicitly yield the processor. And then that notifies the operating system that the processor has become schedulable, and the operating system schedules another thread on it. Or it could be done at a finer granularity event-based, which is also called switch-on-event multi-threading. For example, when you can switch on an L3 miss, right? You can have an L3 miss happen in one thread, and another thread can be scheduled. Now, there's an interesting distinction here. At some point, clearly, coarse-grained has different coarse granularities, as you have seen, right? One is large time quantums. The other is events. Large time quantums and coarse-grained events don't require multiple hardware contexts to be in the same processor, right? But if you start switching on an L3 miss, for example, now it takes a lot of time to change the context because that requires an operating system call, and the operating system needs to remove the existing thread, write its context to somewhere in memory, and then bring in some other thread, read its context from memory, and put it into the hardware structures executing, right? Including the register files, program counter, address translation, basic structures, etc. So if your coarse-grained granularity is actually lower and lower, then you want to keep the thread context in the hardware also. So there's some coarse-grained multi-threading that doesn't require thread context in hardware. And there's some coarse-grained multi-threading that starts requiring thread context in hardware. You need to have basically multiple sets of registers, essentially multiple sets of registers, right? Maybe even multiple sets of TLBs, right? Usually that's not done, but it's possible to do. Okay, so that's coarse-grained. Once you start going fine-grained, as we have discussed in DDCA, fine-grained means, we have also discussed in the last lecture, right? Sun Niagara approach was like this. Essentially, you do cycle by cycle. Every cycle, you switch to a different thread. Clearly, you cannot do this in software at all. You can do switch on L3 miss in software, except it'll be costly. And you also need some mechanisms to signal to the software. Clearly, you need to change the hardware. But here, you have to change the hardware and add thread context, right? Simultaneous is, I guess, somewhat similar to fine-grained. You have hardware thread context, but you don't switch to another thread every cycle. You just keep executing from different threads concurrently. You may fetch from the threads every other cycle, but instructions from different threads are everywhere in the pipeline. Whereas fine-grained means a given instruction, only one instruction can be from a given thread in the entire pipeline. Right? So different threads occupy different parts of the pipeline. Whereas here, simultaneous, everything can be simultaneous in the pipeline. So the difference here is fine-grained multi-threading is a lot easier to implement in the sense that within a thread, you don't need any dependency checking. Whereas simultaneous, within a thread, you need to have dependency checking because you cannot guarantee that multiple instructions from the same thread are not present in the pipeline at the same time. Right? Okay, so clearly today's processors have simultaneous multithreading. Intel calls it hyperthreading, which means nothing, I think. I guess it's hyper compared to coarse-grained multithreading, yes, but fine-grained is also hyper then, right? Fine-grained is, actually fine-grained doesn't have a good name also, in my opinion, but that's the way things are named. Fine-grained is extremely fine-grained. I would call it cycle by cycle, maybe. Okay, so this is important, and clearly all of these issues that we're going to discuss arise in multithreading as well. But we used to cover more multithreading in past. Well, we still cover fine-grained multithreading, but then I had more multithreading lectures in an earlier class that I'm not going to cover. These are actually very nice, interesting topics over here that we don't have time to cover. If you're interested, you can look. Any questions? Okay. Otherwise, we're going to cover something that is extremely important, I think, when we discuss parallel processing. And that's going to be the limits of parallel speedup. We're going to have some fun. I'm going to ask you to think a little bit. So this is my polynomial over here. Variable AI are actually constants. X's are variables. X is an input, essentially. And this is x to the power of 4, x to the power of 3, x to the power of 2, x to the power of 1. And this x to the power of 0. Well, to be, let's say, complete. So assume that you are given inputs x and each AI. Assume each operation takes 1 cycle, there's no communication cost, and each op can be executed in a different processor. This is the assumptions that we've had earlier, right? Perfect parallel processing. There's no overhead in instruction fetch. Forget about that. There's no instructions. We just schedule operations into different processors, functional units. Then the question, there are 2 questions over here. How fast is this polynomial evaluation with a single processor? And then you assume no pipelining or concurrent execution of instructions, just 1 instruction in the processor, right? 1 cycle in each processor. And then there's no distinction also between instructions. Addition is the same cycle, the same 1 cycle. Multiplication is also 1 cycle. Okay. And then the other question is, how fast is this with 3 processors? Do I go to the next slide? Maybe not. Okay. If you had a photographic memory, if you took a picture of the next slide, then maybe you'll get it right. Okay, I'll give you a couple of minutes. If you want, you can rewrite the expression. Well, assuming, basically, I want to compute this polynomial. As long as you get the result right, I'm not going to say I don't care how you do it, because you may get lucky in getting the result right. But I want you to still compute this polynomial. Yes, you have a question? Or no? Okay, it got answered? Yeah, no, that's not given. Yeah. Only X is given. Only AIs are given. Yes. I'll let you work through it. This is fun. Let's see if we can achieve consensus. Let's see. Let me see first and then. Let me see. Yeah, maybe you can switch it. Let's see how this works. Well, we can overlap the latency of switching. Don't go to the next slide. Didn't start. Okay, it started. Maybe you need to stop sharing. So this is it. Okay, I'm not going to show anything yet. Oh, well. Let's see. Did anybody complete it yet? Not yet. We can wait a couple more minutes. No using ChatGPT. I should have said that earlier. I wonder if it'll get it right, actually. I'm curious. If it studied my old lectures, maybe it'll get it right. Okay, go ahead. What? Say it again. Two what? I couldn't understand that part. Two in two. Like 2 by 2? Mm-hmm. Yeah. Yeah, I mean, that will be tightly coupled in that case, assuming those two RISC-V cores are part the multiprocessor that actually have the same global address space. But it doesn't have to be tightly coupled. It could be a RISC-V core on Mohammed's laptop and another RISC-V core on my laptop. Now, if you partition the program across those, they don't share a global memory address space, right? So it really depends on where those RISC-V cores are. So it's not a function of RISC-V, clearly. It's really a function of whether the parallel processors share a global memory address space. Okay, anybody? Any answers? There's one person who has an answer. There's another person who has an answer. 3 people. Are we getting answers from more? 4? Are there more? Don't tell the answers yet. 5, okay? Do we wait 1 or 2 more minutes, or do we start collecting answers? I'll wait 1 more minute. Okay, let's start collecting answers. Anybody wants to volunteer? So the first question was actually, how long does it take to execute this polynomial, which you don't see on a single core, single processor, not core? 12 cycles, 8 cycles. What? What? 11, okay, 12, 8, 11. No matches so far. 9, 14. Did you just make it up? No, 14. Because I don't know how you can get 14 on this one, but fine. Anybody else? Also 11. 10. 11. Anybody else? Clearly, you won't be outlier with these because there's no outlier. Nobody else wants to volunteer? There's no embarrassment, don't worry. But there's only one correct answer, actually. So maybe none of this is correct. But I think, who said 11? 4 people. Are you sure? Okay, I didn't count, so it doesn't matter anyway. This is how you would get 11, I think. Well, you could get it in a different way, perhaps. How do we do this? Actually, I don't think I need this. I was going to construct all of this, but we don't have time. So maybe we go back to slides. So 11 was the majority, right? A majority is always correct. That's how democracy works. Fortunately, in science, we don't have to be democratic. All right. Thank you. Sorry. I thought I was going to write, but maybe I don't need it. So 11 is the correct answer, according to the majority. And this is what you get. This is how you get 11, I assume, right? You try to do this. Basically, you take, essentially, there is you multiply x twice, you get x squared. And then you multiply it one more time, you get x cubed. You multiply one more time, you get x4. And then you input a, and then you get input x to the power of 4. And this is the a4 x to the power of 4 over here. And then you compute a1 x1, a2 a1 x a1 a2 x squared, a3 x cubed over here. And then you start adding a2 x cubed over here with a4 x4, and then you add a2 x2 to it, and then a1 x1 to it, and then a0 to it, right? You have 11 operations. Another way of doing it is basically one operation here. So there's no operation. Anyway, you basically count the number of operations. 11 cycles. Sounds good. Now, what about the 3-processor version? There was another question. How many cycles does it take with 3? We're going to get to it. I think the majority is always right. So you have no voice to speak in a democracy. For one interpretation of democracy, I should say also. Let's not get into politics, but that's one interpretation of democracy, which is quite flawed in my opinion. But anyway, okay, 3 processors. I want to collect those answers. Nobody did it? You just did it for 1? Yes. 6? 6, okay. 5? Okay, now this is not an auction, you know. Well, I don't know. Yeah, that's right. It's the lowest wins in this case. You're right. Anybody else? 6, 6, 5. I have. So more people did the single-threaded version, which also shows something. It's easier to do a single-threaded version, or maybe you forgot. I don't know. Maybe you forgot that there were 2 questions. Should I give you more time, or? Okay, I'll give 1 minute. So far, 6 wins. I want some people to tip the balance. All right, I'll give you 1 minute. I want an answer from the person who got 14 for the first one also. Okay. It's no, it's fine. We still haven't ended things yet. But yes, I think you pointed to another flaw of democracy. You cannot change your vote after you voted. Doesn't matter anyway who you vote for. Okay. Can I collect more answers right now? Yes. 5, another 5. 6, 6, 5, 5. Or maybe you're between 6 and 5, 5.5. That doesn't work with the rules though. Anybody else? Nobody else computed during this time? That shows you the difficulty of parallel programming. Okay, if you're not going once, yes, you have it. Maybe 6. I like this approximate answer, maybe 6. Okay, so the majority says 6 then. Is that true? Yeah. Okay, so the majority won in the parallel single thread case. That was 11. Hopefully no one has an issue with this 11. I have no idea why someone would get 14, but we can figure that out later. How did you get 14? Oh, I see. Yeah, but if you look at this, no communication cost, each op can be executed in a different processor, assume each operating from one cycle. It doesn't say anything about fan out. Yes, you assume something about fan out. Well, you were wrong as a result. Okay, I get 5 with 3 processors. And this is how I would do it. X square here, A4X square here. And this is A2 plus A4X square here. And X square goes also here. And then this A3X. And this is A3X square here. And this A1X. And then A0. A1X plus A0 plus A3X3. And you already have whatever I just said over here. A4X square plus, yeah. Okay, anyway. Yeah, exactly, yes. A2X square plus A4X4. And then plus. Did you get it this way for those who got it 5? Yeah, okay, good. So let's compute speed up. So T3, 3 processor time is 5 cycles. Single processor time is 11 cycles. So the speed up you get with 3 processors, 11 divided by 5. So 2.2. Not a linear speed up with 3 processors, but not terrible, I guess. Optimistic, what do you mean? Yeah, sure. Is this a fair? No, that doesn't answer my question. My question is this a fair comparison? This is when the minority wins. It's absolutely not fair because the single processor algorithm, even though the majority suggested that 11 is the right answer, it's not the right answer. So an informed minority, maybe, we'll get to that, at least me, but you probably also, would say you revisit the single processor algorithm with what you learned in high school. How many people learned Horner's method in high school? You learned, there you go. You learned also? How many people did, I'm curious actually, seriously, how many people learned and remember, of course, Horner's algorithm? Not remember to the point of using it, but to the point of like you actually learned something like Horner. Okay, how many people did not learn? They're pretty sure they didn't learn this. It's also good to know. You're pretty sure? Okay, you didn't learn, okay. And you're pretty sure? Okay, it's good to know. I mean, yeah, it may depend on the high school, it may depend on the time, etc. But basically, this guy Horner wrote a paper in 1819 and talked about how to actually solve this sort of polynomial equations nicely, or numerical equations generally, sorry, I won't get to it. But basically, what you can do is this. I will not go to Horner's algorithm, but essentially you first do this, A4X plus A3, and then take X out. Essentially, you progressively take X out. Right? And by doing so, you reduce some of the computations you do, right? You're really, in a sense, you're doing some sub-expression elimination, right? You can think of it that way. And if you do this, you would get 8. You got 8, right? Okay, and nobody else got 8? And you did this, essentially. Okay, And this is a much nicer version of the algorithm, as you can see on a single processor. So now your speed up is not 11 divided by 5, it's 8 divided by 5, and you get 1.6 speed up. So maybe the multiple processor is not looking that good. And we also made a lot of idealistic assumptions about this processor. And this is actually a really important thing to think about. So let's talk about this. So there are implications of this. Clearly, there are a lot of interesting things that happened over here. One of the interesting things was clearly fewer people answered the question for the 3-processor case, which kind of indicates maybe, I mean, it was not a fully controlled experiment, so I cannot say, but it indicates the difficulty of the problem. And the second is most people didn't get it right, which also indicates that there is some difficulty here, right? And this is true even on a lot of algorithms. And think about more complex programs, actually, right? It becomes much, much worse than this. So basically, the key point, actually, before I go into the superlinear speedup is, key point is this comparison is not fair. Well, 11 divided by 5 was not fair. It inflated the benefits from technique, parallel technique. And the reason it was unfair was it was not using the best algorithm for a given processor, a single processor. So we were using actually the best algorithm for a multiprocessor. This was the best way of doing it. I don't think you can do it with 4. Good luck. But we were not doing the best thing for the single processor. And this is an important fallacy to avoid. Yes? It was pretty fair for the multiprocessor. We had no communication, 1 cycle. Fine, yes, that's right. But that's a different question. The question is whether this is fair or not. I will ask the exact same question to your whatever your favorite embarrassing the parallel program you bring. The same question applies. Are you doing the fair comparison? Right? Okay, so essentially the comparison is not fair. And if you don't do fair comparisons, then you may actually build something that is not necessary or not good. And someone can actually do much better than you if they optimize your software. So there are a lot of interesting things to think about here. Okay, so one way of actually thinking about this is essentially, we've seen this graph before, right? Speed up graph. You have number of processes on the x-axis, parallel speed up compared to single-threaded version on the y-axis. And typically, the curve you get is like this. It goes down, actually. This is not the best curve, unfortunately. Typically, you get sublinear speed up for reasons we've discussed last time, right? Sometimes people get superlinear speed up. And usually that's due to 2 main things. Whenever you see superlinear speed up, you should be extremely wary. Whenever you see linear speed up, you should be extremely wary also. Close to linear speed up also, etc. But it's possible at least. I think superlinear speed up is not possible unless you're doing something wrong, like unfair comparisons. Like compare the best parallel algorithm to wimpy serial algorithm. This is unfair. And we've seen companies do this also in the past. I will not name them here. To sell their products. It's amazing the lengths to which companies will go to sell their products. This is probably maybe not as bad. Okay, anyway. But then there is actually a real case where you can get superlinear speed up. Anybody think of that? Yes. Okay. Can you be more clear? Yeah, okay. Okay, yes. Yes, essentially cache and memory effects. Basically, this comparison assumes that you're not adding anything else other than processors, right? But when you're adding a processor, if you're also adding more cache or more memory, then you may get fewer misses in cache and memory. So you don't go to memory as much anymore because you parallelize your problem, not just from a computation perspective, but also a cache perspective. Now, instead of having 1 megabyte cache on chip, you have 10 megabytes cache on chip, and you never go to memory, right? With a single processor, you have only 1 megabyte. You could also say this is an unfair comparison. Maybe you should be comparing to a single processor with a 10 megabyte of cache, but there may be good reasons that this may not be possible if you're doing a real system, for example, comparison. So this is real with cache memory effects, you can actually get superlinear speedups. Hopefully, you're not getting them because of unfair comparisons, though. Okay, so hopefully this was a useful exercise, even though it took some time. And whatever we experienced here is real. In real life, it's actually much more difficult. Okay, so I will also mention some metrics over here. There's some traditional metrics that we use to evaluate processors with, multiprocessors with. And these metrics assume all P processors are tied up for parallel computation for some amount of time. We still have time, okay. Utilization is how much processing capability is used. It's really the number of operations in the parallel version divided by how many processors you're tying up for how long. Redundancy is how much extra work is done with parallel processing, and there's almost always extra work in parallel processing because you need to divide the tasks. You need to maybe replicate the inputs, etc. This is number of operations in the parallel version divided by number of operations in best single processor algorithm version. And then efficiency is basically time with one processor divided by how many processors you're tying up for how long. Efficiency is also utilization divided by redundancy. I will not go through this in detail, but it's good to think about this, like pictorially especially. So utilization basically, in this particular example that we've seen, we were tying up, let's say, we had 10 operations in the parallel version, and we took 5 time units. We were tying up 3 processors, that was a given, for 5 time units, assuming you tie up all of them, because you don't know how long each of them will take, right? This also shows a load imbalance across processors over here. X means you're utilizing the processor at a given point in time over here. So basically, our utilization is really two-thirds, as you can see, 10 over 15. So these are kind of not used. You could allocate them to a different thread, but you need to know that they're done. That's good to know. How do you know they're done, right? So this is the load imbalance problem, as we have seen earlier, right? So this simple example gives us a lot of problems. So redundancy is operations with the P processors, best number, 10. Operations with one processor, as we have seen, to 8. And redundancy is always greater than or equal to 1. Whenever you do parallel processing, you increase the amount of work that you do. In this case, it's not bad, but it's still more than 20%, right? 25%, actually. Efficiency is basically how much resource you use compared to how much resource you can get away with. Essentially, we're tying up one processor for, I guess, T1 time units. My terrible writing over here, I had to correct. And then you're tying up P processors for TP time units. You can really get away with 8, tying up 8, one processor for 8 time units. But we're really tying up 3 processors for 5 time units. So our efficiency is actually close to half, let's say. Not so great. If you're not, well, once you start looking at this metrics, these actually show that you're actually wasting a lot of resources in this particular problem, right? With all of these assumptions. Okay. We've covered some of these, so I'm going to go through some of these very quickly. We've seen Amdahl's law, right? And we've seen Amdahl's law is really about the serial bottleneck, but just to show you some pictures, again, with my handwriting, there's a parallelizable fraction, and there's a non-parallelizable part over here. You can derive Amdahl's law based on this time with P processors. Time with P processors is really parallelizable part times time with one processor divided by P, assuming it's perfect parallelization, plus non-parallelizable part times time with one processor. Right? Amdahl's that equation that I showed you comes based on speed up. This is speed up with P processors. You do T1 divided by TP. TP is this. T1 is T1. And then once you actually simplify the equation, this is what you get, which is essentially the same as what I showed over here, except F and alpha are the same. And if you take the limits of this as P goes to infinity, you get 1 divided by 1 over alpha, and that's the bottleneck for parallel speed up. Now, if you start drawing things nicely, this is 1, this is P, this is the speed up, and these are the speed up curves that I drew clearly with my hand. You could draw this nicely with some other program. But you can see the key point over here is adding more and more processors gives less and less benefit if alpha is less than 1. Parallelizable part is less than 1. So you need to be really close to 100% parallelizability if you want to see more and more benefit. And also, this is another way of looking at it. This is basically a parallelizable part, and this is speed up. The benefit is small until you get closer to 1. And this is another, I'm going to actually, I should have another better way of, okay, this is a better one over here. This is the parallel fraction, F, and this is real numbers using Excel, and use Excel's terrible baseline graph. You can see that the speedups become larger when you get really close to 1, right? And the differences between different number of cores also become more interesting as you're very close to 1. So you want really embarrassingly parallel applications, as you said. Okay. So and we have also discussed that there's parallel portion is also not perfectly parallel, and these results don't take into account synchronization, load imbalance, resource sharing. So it's good to think about this. This is exactly why Amdahl said we should be focusing on the single processor. This is 1967. And there's still good reason to focus on getting that single processor extremely fast and efficient. And scheduling code that requires that fast speed and efficiency on that single processor. Okay, we've already seen a lot of this, so I'll go through this relatively quickly again. We've seen the sequential bottleneck in the last lecture, right? And main reason for this is non-parallelizable operations on data. For example, if you have non-parallelizable loops, where you have a loop carry dependency, you don't get this beautiful parallelization. You need to have some serialization. And there are other causes. Single thread prepares data and spawns parallel tasks. We've discussed this yesterday also. And this is usually very sequential. So this is an example from a paper you're reading. So I will not go through this again in detail. But here, for example, there's a critical section. There's another critical section. There is a parallel part. And this part is serial. And this part is also serial. And this is what the execution time kind of looks like. Serial portions look like this. And then parallel parts look like this. And then critical sections are the limiters. This is, again, from the paper that we've discussed yesterday. We've also discussed bottlenecks in parallel portion. Again, I will not go through this in detail. This is just an overview. Essentially, synchronization operations manipulating shared data cannot be parallelized, so you need locks, mutual exclusion barrier synchronization. I also said yesterday that this is also a communication. Essentially, whenever a task may need values from each other, you need to synchronize them. You can think of this as communication or synchronization, basically. And we've already discussed that. This is called thread serialization when shared data is contended. We also talked about load imbalance. This is either imperfect parallelization or microarchitectural effects. Parallel tasks may have different lengths. And we've already talked about resource contention a lot in these lectures. Parallel tasks can share hardware resources, delaying each other, right? Okay, I think we've seen a lot of this. I'm going to skip a lot of this. I'm going to talk about something else, which is at the very end. This is just for your review. We actually covered this. Okay, this is it. Basically, you've seen all of these difficulties, right? Serial bottleneck, synchronization bottlenecks, resource contention, etc. Essentially, if you're embarrassingly parallel, you have little difficulty in parallel programming. If the parallelism is very natural. For example, you're updating pixels on a screen. It's completely parallel, right? Unless you're manipulating pixels together, you're basically completely parallel update things. Physical simulation has a lot of parallelism, right? If you're actually modeling things, that part of the room has nothing to do with this part of the room, for example. There's a lot of parallelism as long as you can divide your work such that things that do not interact with each other at a fine grain are separated to different processors. You have a lot of parallelism in that problem, right? But now, if difficulty is really in problems where this doesn't exist, this embarrassingly parallel things exist. First of all, you need to get parallel programs to work correctly, even if they are embarrassingly parallel. And if they're not easily parallelizable, you need to optimize performance in the presence of bottlenecks. And as a result, much of parallel computer architecture is really about designing machines that overcome the sequential and parallel bottlenecks to achieve higher performance and efficiency. That's one part. And the other part is really making the programmer's job easier in writing correct and high performance parallel programs. So what we're going to explore in the next lectures are going to actually, we've already looked at the first part, right? At least some of the techniques that are used to overcome the sequential and parallel bottlenecks. We're going to see maybe more of that. But now we're going to focus a little bit more on making the programmer's job easier in how to write correct and high performance parallel programs. Well, the first one actually helps that clearly because the programmer doesn't need to put as much effort But there are some fundamental things that you need to provide in hardware so that you can actually synchronize across different processors. So there are some readings that we've covered that I'm not going to talk about. Let me see how much time we have. We don't have time. Okay. Any questions? So I'm going to leave these slides. I'm not going to cover them in the next lecture, but this basically looks at task assignment for process that we briefly discussed, but you can look at them on your own. They're not that hard. It just covers some interesting trade-offs. If there are no questions, we can end early today and you can enjoy the winter. Okay, I'll see you next week.
Okay. Let's get it started. Welcome everyone to another lecture of computer architecture. Today we're going to discuss two interesting topics. Memory ordering is going to be the first topic that we're going to start, and then we're going to get to cache coherence. All these topics are actually coming up when we want parallelism, when we are using multiprocessor and multi-core systems. So that's why we are covering such techniques after the parallelizing lecture. Okay, so I'm going to start today's lecture with this recall from last week. So essentially, we were discussing about difficulty in parallel programming. And we say that there is little difficulty if parallelism is natural, like when we have embarrassingly parallel applications, like multimedia, physical simulation, and graphics. But we have difficulties in basically when parallel programs to work correctly. And when we want to optimize performance in the presence of bottlenecks. And in the end, much of parallel computer architecture is about designing machines that overcome the sequential and parallel bottlenecks to achieve higher performance and efficiency, which we have discussed a lot, like last week, with bottleneck acceleration, for example. And another point is that making programmers' job easier in writing correct parallel programs, not even high performance. So we're gonna focus a lot how can we make things correct, but then we're also gonna see a little bit how we can make things high performance. So essentially we have this trade-off between performance and correctness, and we have seen it a lot in this semester as well. So these two metrics, they are fundamentally at odds with each other, as you can imagine, and you can always improve performance at the expense of correctness. For example, you can say that I like to multiply two numbers or two vectors, two matrices, for example, and then you're going to guess the output. You're not going to compute. So that, of course, is high performance, but probably not that accurate. So that's of course, this is quite kind of exaggeration, but essentially you can actually make some trade-off by guessing, by speculating, and provide better performance. But at the same time, you need to make sure that you are not doing something wrong. So for example, we can forget some critical logic in your program. We discussed also a little bit this in the last session, that essentially you can, for example, speculatively execute some critical sections, assume that there is no conflicts. Like we assume that there are not, there is only one thread in the critical section. And then we had to check at the end of the critical section that what we have done is correct or not. And then it's not, if it's not correct, we need to redo things. So these things can be important, can provide better performance, but at the same time, you need to have some technique in order to recover from the execution which was not correct. Or for example, we can design our architecture to ignore ordering of operation. We're gonna see today actually about that. And we're gonna see examples in fundamental support in multiprocessor operation, MIMD, like memory ordering and cache coherence today. But I like to also mention that there is also sometimes a real trade-off between performance and correctness. There are some applications that you are okay with, like reducing correctness by some definition, and then to provide better performance. Any thoughts? Or any example you might remember from this course? Yes? Yes, and in which work? We discussed some of them actually. Do you remember? Anyone? Do you remember Eden? Yes. Yeah, Eden, for example, is one of them. That basically we show that we can improve DRAM energy and performance by making DRAM a little bit faulty, but hopefully for those layers or for those parts of your data that they don't need exact correction, you can use this trade-off essentially. So Eden is one of them. Heterogeneous reliability memory in DSN14 is also another one. And of course, you can check these papers. We already covered them. So if you're interested, you can take a look. Yeah, but this is, when you think about performance and correctness, it's also very similar to the latency and reliability trade-off, essentially. So reliability is at the hardware component level, like each component is reliable or not, but correctness is at the program semantic level or hardware function level. So if you think about it, there is actually a very nice analogy between them. So there are also some ideas, that you try to make a latency reliability, like Eden actually. Eden make DRAM a little bit unreliable, but provides better latency. But when you think about use of Eden at the application layer for neural network, let's say, then you are actually also considering this correctness issue. So you need to always consider these both trade-off here. And of course, we have seen examples of latency reliability trade-off before, like lecture 9, memory latency, these are actually from previous lectures, but you can see the links to the YouTube later. We also show that, for example, sometimes you can use these trade-off for doing something useful, like this for a DRAM PUF, that, for example, you can, when you violate timings, there are some cells that they always fail, and you can use them as a signature of your device, for example, for this. Or you can use them to use a kind of basically trade-off in order to provide random number generation in this work, and also quark TRNG in other one. But now today we want to look into memory ordering in multiprocessor, which is actually very important in order to make sure the correctness of the execution. And we don't want to make trade-off here, essentially. So we want to make things correct. But we can also try, we will also release basically relax the model a little bit in the end. So these are required readings for this topic. We have this basically 2-page paper from Lamport, which is the concept of sequential consistency is proposed or defined in this paper. So I would like to suggest you check. Actually, it's going to be one of the readings as well, one of the required probably. But there are also some recommended readings that we're going to also discuss them a little bit today. You can check them for memory consistency. So let's start with some definition. So what is memory consistency and what is cache coherence? We're going to see cache coherence also later today, but it's good to know about them in the beginning. So consistency is about ordering of all memory operations from different processors. So first of all, we are considering several processors. It's not only one processor. So we have multiprocessor system or multi-core, and then we want to, we care about the order of all memory operations that's coming from different processors. Or essentially, these operations are from different memory locations. They are not looking into one location. So this is the topic of global ordering. So global ordering of accesses to all memory locations are important in the consistency, memory consistency topic. Related to this topic, we also have coherence, but with a little difference here, that coherence is about ordering of operations from different processors to the same memory location. So basically in coherence, we care about local ordering of accesses to each cache block that we're gonna also see today. But we're gonna start with consistency, as I said. So we discussed about this much of a parallel computer architecture that is about designing machines to overcome sequential and parallel bottlenecks, and also make program job easier in order to write correct and high performance code. So this is basically the problem statement for memory consistency. We have operations A, B, C, D. They can be memory operations. In what order should be the hardware execute and report the result of these operations, essentially? So that's the question about memory consistency. So there should be a contract between the programmer and microarchitecture that is specified by ISA. And then that protocol preserve an expected, or let's say more accurately, actually, agreed upon order that simplifies program's life. So once the programmer knows that the ISA will obey some rules or some protocol, then basically you can expect, you can see that, okay, you can basically make some, you can have some expectation about how these things are gonna run. So of course, why is it important? You can guess, is because of ease of debugging. So if you don't know what's going on, you don't know, and so you run your application and you see that, okay, semantic is wrong. And then you want to debug it. But the second time that you run it, there can be, actually your program might work because of some orders that you don't know, right? So once you know that, okay, which orders are possible or which are not, then you can actually have better debugging. Also, about ease of state recovery and exception handling. You might remember from the DDCA course, Digital Design Computer Architecture, that we discussed about precise exception. Once you have exception or interrupt in your execution, in out-of-order execution, you need to have the precise state such that when you're done with that exception, you should know that in which state you need to come back, essentially. So these are really important in order to provide, otherwise, essentially, again, it also goes to correctness and the difficulty of debugging. But of course, when you want to provide this kind of expected, it usually makes the hardware designer's life difficult. But it's very important for programmer perspective. So you need to make things also easier for them. So in the end, it's a trade-off again between programming and hardware design. So you need to see which, for this topic, how much we need to make programming life easier, how much we need to make hardware life. We're gonna start from a model that makes the programming life very easy, but then we're gonna see that that model is actually quite costly. And then we're gonna get to the model that show that, okay, programming can actually, you can make the programming life a little bit harder, but at the price of, as a reward of a lot of good, less basically overheads in the hardware design. Okay. So let's see about memory ordering in a single processor first. You know that is specified by the von Neumann model. We have sequential order in a single processor, essentially. So the hardware executes the load and store operation in the order specified by the sequential program. Even though you might have out-of-order execution, but out-of-order execution does not change the semantics, because in the end, you retires execution, retires instruction at the order of programs, essentially. So that's why we have this reorder buffer, for example, that to make sure that things are happening in the sequence of the program. So these are like advantages of that. Of course, you can see that the architectural state is precise within an execution, which is, I said, why it's important to have precise state, especially when you have exception or interrupt in your application. Also, the architectural state is consistent across different runs of the program, which again is important. So when you see an error, you want to basically reproduce that error such that you can debug it. But if you see errors randomly, it's very hard to, to originate, localize the error and fix the program, essentially. But of course, it comes at some disadvantages. Like we need to preserve order, and that adds overhead. Like this instruction window that we have, this large instruction window, reorder buffer, all these things are there and provide overhead. Adds overhead to the design. And they also reduce performance at the same time, because at some point you need to, in order to ensure the correctness or in order to obey this sequential execution, you cannot, you need to sacrifice performance sometimes. So you need to stall. And also it increases complexity and reduces scalability in the end. So you can also check our lecture in this link below of DDCA for this stuff also. But now also let's see another extreme of this, which is data flow processor. You might also remember data flow processor from our DDCA course. How many of you actually take our DDCA course before? You? Okay. Yeah, but you can, other also can check these links if you're interested. Okay, so in data flow processor, basically, you know that memory operation executes when it's operands are ready. Essentially, in data flow architecture is that. So there is no instruction basically control. So you have operations, and each operation has some operands. And when the operands are ready, you just fire the instruction. So it's true data flow. And as I said, ordering is specified only by data dependencies. So that's the only dependency that you need to consider. And of course, yeah, two operations can be executed and retired in any order if they have no dependency. So that's the thing. So it's very hard to basically reproduce or so when you rerun a data flow architecture, the order of instructions might be completely different because there are not many instructions are actually dependent on each other and they don't have data dependencies. Many of them, they don't have data dependencies and you can just run them in any order in data flow processor. So of course, it's very good because it provides lots of parallelism and high performance, but unfortunately, there is no precise state or ordering semantics. So essentially, it's very hard for debugging. And also, you cannot easily recover from issues, essentially. Okay, but now let's see memory ordering in a MIMD processor. So we know that each processor's memory operation are in a sequential order. So each processor actually obeys von Neumann model. So we know that. With respect to the thread running on that processor. But now we want to see if we have multiprocessor and each processor obeys von Neumann, if everything is bright or we might run into some issues, essentially. So how does the memory see the order of operations from all processors? Or in other words, what is the ordering of operations across different processors? And if it matters in the end. So why does this even matter? There are three reasons of that: ease of debugging, correctness, and performance on overhead. So for ease of debugging, it is useful to have the same execution done at different times to have the same order of execution, which is important for repeatability. So even though this is really important, but many of actually parallel processors like MIMD architecture, they don't really provide that. There are actually some works that you can record and replay. Like you record the sequence of instructions or sequence of memory operations when you're running in a debug mode, and then you replay from that in order to see the problems, essentially. So you can replay from your record. But normally, without that support, you don't really have basically, you cannot have the same execution done at different times. So depending on how cores are busy, what's the status of your memory, what's the status of your pages in the memory. So there might be many different orders, essentially, across threads. So in the end, when you work on multiprocessor and parallel programming, debugging is always a hard task. And if you write a parallel application, I guess you can tell that. Essentially, it's not really easy to debug your code. But correctness, we want to provide that. So can we have incorrect execution if the order of memory operation is different from the point of view of different processors? So we're going to see that this is bad. So if different processors observe different orders, that shows that there is an issue in your execution. And we're going to see with some examples. So it's really important to not run into this issue. So we need to make sure that there is no incorrect execution in such cases. And then performance and overhead, like we can enforce a strict sequential ordering that we're going to see actually, that can make life harder for the hardware designer, but is actually easier for programmers. But that you can see the overhead here, like the trade-off. So that kind of a strict ordering will add a lot of overheads to the design, and especially like the whole design components, like your architectural components, like out of order execution, caches. So once you have caches, for example, not many, so there is a local cache, and many of operations from that processor to that cache is not observed by other processors. So now if you want to have a kind of sequential order such that all processor knows about what is happening, so you need to communicate all information. And that complicates a lot of things, which we're going to see a lot today. So we're going to focus a lot on correctness first, and then we're going to also see how we can reduce the performance overhead in designing this. So essentially, this order affects correctness when we are protecting shared data. If you are operating on private data, like assuming that you are like updating some pixels, and each processor or each each processor or each thread is operating on some local pixels essentially. So those can actually work completely independent, and you don't really care about the order of memory operations. But things are important when you're operating on shared data, and then the order is important. Like if you are sending several writes, like which write is actually should be earlier or later, essentially. So as I said, protecting shared data is important. Threads are not allowed to update shared data concurrently for correctness purposes. And that's why we have these accesses to shared data are encapsulated inside critical sections, for example, or protected via synchronization constructs like locks, semaphores, condition variables, that they can actually lead to critical sections in the end as well. So we know that only one thread can execute a critical section at a given time, which call it mutual exclusion principle. So we want to see that actually, so this is at the software basically level. We want to see that if you write a code which is correct at the software level, so you have done a good job in making these critical section logs and handling them. But if you run that code in the hardware, is it gonna work or not, essentially? So a multiprocessor should provide a correct execution of synchronization primitives in the end. So these are primitives like logs to enable the program to protect shared data, essentially. So you need to provide the support, good support for these, essentially these synchronization primitives in the hardware. Any questions so far? Okay. So programmer needs to make sure that mutual exclusion is correctly implemented. We will assume this, even though it's not really easy, and there are many works going on there. But essentially, correct parallel program is an important topic, as I said, and you can check this Dijkstra work. Is actually one of the basic of this topic. I'm not sure if any of you have read this paper. But yeah, this is actually one of very basic work, like basic content of this. So if you want to work on parallel programming, essentially, you cannot avoid Dijkstra. So you need to, of course, check this paper. But you might be aware of Dekker's algorithm for mutual exclusion. Okay, so we're gonna use Dekker's algorithm actually in this example, but of course there are many other also way to provide synchronization across different threads. So essentially, programmers relies on hardware primitives to support correct synchronization, and we want to see that if that's happening or not. Question do you have? Okay. So if hardware primitives are not correct or unpredictable, then programmer's life is tough. If hardware primitives are correct, but not easy to reason about or use, then still programmer's life is still tough. So it's very important that you provide, at least you need to provide a contract from the hardware from the ISA to the programmer, such that programmer knows what to expect. But those also should be easy to understand. So that put a lot of basically difficulty in design such processor. Okay. So I want to explain this with this example here. Assume that we have two processors, P1 and P2, and you have two synchronization variable, F1 and F2. Both of them are initialized to 0. After some time, and you have a critical section here, and essentially you're controlling the access to the critical section by these synchronization variable, essentially. So this processor set F1 to 1, meaning that I want to enter the critical section, but this needs to test the F2 variable. It can enter critical section if the other one is not in the critical section, meaning that F2 is 0. So this tests F2 is 0, and then if it is 0, then it can enter into critical section. And at the end of that, it needs to reset the this synchronization variable such that the processor P2 can enter it if it's waiting for that, essentially. And the same thing is happening at the P2 processor, with the difference that it sets F2 to 1. So you need to use different variables. And it also checks the F1, essentially here. Question? This is very simple Dekker's algorithm. So this can work, right? Yes. It can what? Yes. But we don't want to discuss those kind of issues now. But yeah, it's not the best way of actually providing this synchronization. That's why I said that at software you need to actually implement a lot of, like, there are different levels of providing this synchronization, and you need to work hard on that. But we think that this is okay. But now we want to see how this might not work in the hardware, essentially. Okay, so the question is that can the two processors be in the critical section, which should not happen at the same time, given that they both obey the von Neumann model? So that's the question, and this is the baseline we consider. So if you consider that you have two processors and then there is interconnection network and there is one memory here, this might work. But if your memory is banked, then you can see that this might not work. And we're going to see with this example. Okay. We also actually have a DokuCam here, but I don't know. Okay, let's walk through this example together. This is the y-axis for the time, and then we can basically see check this scenario. So P1, first, it needs to set F1 to 1, basically, right? F1 set to 1 and complete from P1's view. So basically, P1 set that 1 and then retires the execution. So, and then A sent to the memory. So this A is like set F1 to 1 is already sent to the memory, and from the processor 1's perspective, this is done. Here also the same thing in parallel. P2 assume that it reached to this X. We call this instruction X here. So these two A and B instruction, and these two are X and Y. So P2 also executes instruction X, meaning that it set F2 to 1. And then from processor 2 also point of view, you retire this instruction, essentially. And you send this X to the memory, essentially. So later on, you reach to that. So P1 reach to this B instruction, which you need to test the value of F2. So you need to test F2, meaning that you send this read request to read the value of F2 from main memory, essentially. And now P1 is stalled, actually, there, because P1 doesn't know the value of F2. The same thing happened also for P2. In P2, you need to test F1, but F1 is, so you don't have it, you need to request from memory. So you send it request from the main memory, and then you're stalled here, that instruction. So after some time, memory sends F2 to P1. But this can happen actually before that write. Before that write actually takes place in the main memory. So from the processor view, you're done with that instruction because you already commit that instruction, right? But it hasn't done eventually can happen, can be done, but so far it hasn't done in the main memory. Like in the main memory still have the absolute data, let's say, 0 and 0. So memory basically replies to your read operation and then sends basically 0 essentially sent to the P1. And then P1 can enter the critical section, right? Because this F2 is 0. So exactly, since if F2 is 0, P1 enters critical section. The same thing can happen also for the processor P2. So memory replies with 0 to P2, and then P2 enters critical section. Then after some time, memory completes the operation A, and F1 is now 1. And also in this side, also memory completes operation X, and F2 sets to 1. But these are clearly too late. So this can happen. Also, if you know that like these two operations are load, essentially, right? And in many actually cases, for example, in interconnection network, people come up with a lot of prioritization techniques. Like you want to prioritize reads over writes usually, because they are on the critical path of execution. So it's actually kind of possible that you receive your read operation earlier than your store operation, essentially, even though you issue that store earlier, but you can get your read operation faster. Okay, so this is incorrect. So now we need to see, want to see like each processor's view, what's happening here. So from the processor 1 perspective, this is the order. So processor 1 sends A, right? And then processor 1 sends B. And then processor 1 basically sees X happening in the main memory, right? From the P2's view, it sees that, okay, it sends X and then Y and then A. It's happening from the P2 points of view. So essentially from processor 1 view, you have A, B, X, meaning that you have A and after that you have X. But from processor 2's view, you have X, Y, A, and then essentially you have X and after that A. So these two cannot be correct at the same time, right? So one of them is seeing A before X, the other one seeing X before A. And that's the reason we are saying that in memory consistency, all processors should see the same order. As long as you see the same order, things would actually go correct. You can actually test it. And that's the topic of memory consistency, essentially. So the two processors did not see the same order of operations to memory. And this happened before relationship between multiple updates to memory was inconsistent between the two processors' point of view. And as a result, each processor thought the order was not in the critical, thought the other was not in the critical section, which as a result, things can go wrong, essentially. So that's the problem. So how can we solve the problem? The idea is sequential consistency, which is actually proposed in that two-page paper, Lamport. So all processors see the same order of operations to memory. It's actually quite a strong consistency model. So all memory operations happen in an order called the global total order that is consistent across all processors. So this is really important that all processors see the same order across. And as our assumption here is that within this global order, each processor's operation appear in sequential order with respect to its own operations, meaning that each processor obeys Amdahl's law, von Neumann model. Each processor obeys von Neumann model, which is sequentially consistent, but also beyond that, all these processors that you have, they all observe the same order of operations in the memory. So this you can actually read from this Lamport paper. And these are the two conditions that I already mentioned. So this is actually a memory ordering model or memory model, people call it, and it's specified by the ISA. So this is, but how actually microarchitecture implements that model is another basically issue here. So now we know that this is a model. And once we somehow, basically obey this model in the microarchitecture, then our multiprocessor is sequentially consistent. And then programmer can easily, for example, run this Decker's algorithm and everything would be bright. But the thing is that how we implement that is actually quite also, it's not easy. And that's why we don't really have much sequential consistent processors in the market. because it actually adds a lot of overheads, which we're gonna see, to the design and also to the performance of the system. From the programmer's abstraction, you can assume that in a sequentially consistent multiprocessor, essentially there is a switch between your memory and also the shared bus. So memory only, tries to basically service. Basically, memory services only one request at the same time, and that service is observed by other processors. Essentially, it's very similar to implementing that. Remember that I talked about multi-bank memory and also one bank. So if you have only one bank in memory, like the whole memory is one bank, then you might have similar stuff. But the problem is that your memory is multi-bank, and then you need to provide such kind of illusion, like understanding by providing sequentially consistency. Okay, any question? Good. Okay, so there might be a lot of potential correct global orders, and all can be correct. As we said, we don't really care about debugging here much. We only care about correctness. So if you get back to our example before, you can see that all these orders are possible. And but the point is that each of them is consistent. So if processor P1 observes A, B, X, Y, processor P2 will also observe the same order. And that's the key here. But if you want to make it also easy to debug, you need to make sure that, for example, you always have one of these orders. Or you might have many other orders, but at the time that you have some errors in your program, in semantic, you should be able to repeat the same order. You should be able to control that. And that's why people come up with these replay and record and replay stuff, which is also adds overhead. Okay, so which order, or this also called as interleaving, which order or interleaving is observed depends on the implementation and dynamic latencies. So yeah, there are a lot of dynamic latencies that you can imagine when you want to access your memory. You have interconnection network, you have memory controller. Memory controller has scheduling stuff, queuing. So there might be a lot of different orders that can happen. But the important part is that all of them each order is consistent across all the processors. So these are also another important things to say, like within the same executions, all processors see the same global order of operation to memory. So we don't have correctness issue, just to want to repeat it. And that satisfies the happen before intuition. And across different executions, different global orders can be observed, each of which is sequentially consistent. So debugging is still difficult as order changes across runs. If you want to learn more, you need to check this paper. It's actually not a long paper, it's only 2 pages, but provide that these concepts very nicely. Okay, question? Okay, nice. Okay, so now let's see what are the issues with sequential consistency. So we know that this is actually kind of nice abstraction for programming, but there are 2 issues. First is that it's too conservative. Like for the ordering requirement, our approach is too conservative. And also it limits the aggressiveness of performance enhancement techniques. So once you want to make this sequentially consistent, you need to actually sacrifice a lot of performance improvement techniques. Like, as I said, for example, like caches. Like caches are important in order to provide performance. But if you really want to make things sequentially consistent, you need to communicate the order of all memory operations across all processors. So many of these memory operations are happening actually inside locally. So then you need to actually communicate many things that are happening local in the processor to other. At some point, you want to get rid of caches, essentially. Or if you have cache, you need to communicate all the updates or all the updates that are happening to your cache. I mean, that's also interesting because that's part of the issue that we're going to see today about cache coherence. But from the sequential consistent point of view, cache can be actually filter out a lot of memory operations, and making all processor aware of all memory operations is very hard once you have caches. Clear? Yes.
I don't understand why you sequence all operations. You the operations are shared.
That's so first of all, sequential consistent doesn't say that. So that's why we're gonna relax the model. In sequential consistent, say that the order of all memory operations should be, yeah. And that's because we want to make the life easier for programming. Because once you want to do that, which we're gonna see actually, programmer needs to differentiate between what is shared, what is not shared, right? So
You can have the hardware.
how hardware can decide on shared or not shared?
No, to reduce. I mean, that's something that I didn't think of. But
yeah.
To reduce the overhead from the program. The programmer does not just need to decide which.
No, in the end, it's actually part of the semantic of the program, right? So program knows that, for example, this is critical section, and I want to operate. So this is, for example, my consistency variable, like not synchronization variable, which is important. So I want to make sure that that is happening consistently. But so in the end, programmer needs to do something if you want to do such things. But sequential consistency say that I will make sure that everything is consistent and all processors observe the same order. Then the life is easy for programming. Programmer does not need to do anything, essentially. Just write a code. I mean, of course, programmer needs to write this daycare algorithm, for example. But as long as they write, these simple primitives, things will be bright, essentially. But yeah, but now the question is that is the total global order requirement is like too strong, which I think we all agree that indeed it is. So do we need a global order across all operations and all processors? How about a global order only across all stores? And people actually come up with all these weekend consistency model. We're going to discuss about weak consistency model, but that weak consistency model is not only one thing. There are many works in academia and also industry, the way that people implement this microarchitecture, that they come up, they try to not be that strong sequential consistent. They implement some sort of weak consistency model that we're going to see. So, but this is one, for example, that you can have a global order only across stores, because for a store you might care. I mean, for reads, you don't really care much. And then, or for example, you can enforce a global order only at the boundaries of synchronization, which is actually quite interesting. And we're going to see about that today. And this is actually relaxed memory models. And you can get this, call this consistency model as AQR and release consistency model. So performance enhancement techniques that could make a sequential consistency implementation difficult. So this out of order execution is one example that I already mentioned, that loads happen out of order with respect to each other and with respect to independent stores. So loads are usually happen out of order, right? So this makes it difficult for all processors to see the same global order of all memory operations. And another one is caching, which I already mentioned, that a memory location is now present in multiple places, and that prevents the effect of a store to be seen by other processors, make it difficult for all processors to see the same global order of all memory operations. And we're gonna also see that caching can also cause this coherence issue, but that's relates to one specific memory location. But in the perspective of consistency, like memory ordering, even though you might write to different addresses, but since you have caches, you're not, if you don't communicate that to the whole system, then the whole processor, the old processor do not know the order of all these memories. So that's why caching makes things like providing sequential consistency once you have caching is not easy. That's why people actually came up with this weaker memory consistency model. So the ordering of operations is important when the order affects operation on shared data, meaning that when processors need to synchronize to execute the program region. Weak consistency, this one idea is that programmer specifies regions in which memory operations do not need to be ordered. And this is with memory fence instructions, for example, in some ISAs, that you need to delineate those regions. And all memory operations before a fence must complete before a fence is executed. So before a fence, there are some memory operations. All this needs to be done. And then all memory operations after the fence must wait for the fence to complete. So that's our model, essentially. And this fence is complete in program order. It's very also similar to barrier. In some ISA, actually, they call it memory barrier or so. Okay, question. So this is one example. So like examples of weak consistency model, as I said, this is one way of implementing weak consistency, but people also came up with different ideas in order to weaken the consistency model. This is sequential consistency, which everything should be like this arrow mean that V cannot perform until U is performed. So in sequential consistency, we have arrow basically among everything, essentially. This load cannot happen before this load finish, this store before that load, and so on and so forth. But there are also some other like consistency model that people come up in order to reduce the overhead. This is processor consistency. And people say that, for example, they observe that these store and load things, these two are not needed to be consistent. You can check these papers if you want to learn more. But this paper actually discuss also different ways to provide weak consistency. Here is actually two examples. One of them is a weak consistency model. WC as kind of unfortunate naming. And also release consistency. So in a weak consistency model that we have here, essentially you have this acquire and release. So you need to, and then you have some critical sections. So you acquire the log, and you know that by the definition that we say, everything before that acquire log should be done. So once you reach to this point, you acquire the log, and then you enter a critical section. So in this critical section, you can actually do order, like operate on any order, because these are not your, even this is critical section, but you are handling that, like you are making sure that with these logs, that not only one processor is inside this critical section. So you can actually operate them, you benefit from your out of order execution. That being said, we still need to obey von Neumann model. But with that, you don't need to care about much. So things, you don't need to make sure that things are sequentially consistent across all processor inside this critical section. The only thing which is important is this acquiring log and releasing logs. Those should be consistent across all processors. And then after this releasing, you have also a code here, which is not a critical section actually. But then this also doesn't need to be sequentially consistent. Then here you have another critical section, but this critical section needs to be, again, you need to acquire log, essentially. So these two needs to be acquired. So this is a weak consistency model that this paper discussed. But people also look into it like a little bit more, and they come up with this release consistency technique, which actually quite interesting. It's kind of actually obvious. But at the same time, this release consistency is very hard to implement. So not many processors today actually have that, maybe none of them, which actually I'm not aware. But in release consistency, you can see that in order to, assuming that these operations, these blocks, like block 4, block 2, and block 6, they might have a lot of out of order execution, like independent instructions, right? They might have. But the problem is that you cannot execute them. You cannot benefit from out of order execution because you are running them in a sequential way. You know, you acquire a log, you run this, then you release the lock, then you can go to this section, then another lock, run this critical section, and then release the lock. So all these blocks, block 2, 4, and 6, are happening in a kind of sequential order, essentially. But they might have some instructions that they are independent, right? So with this kind of graph, you can actually try to run them in parallel as much as possible. So running basically a block 4 needs only basically acquiring lock A, essentially, right? No, but the thing is that if it's not related to your shared stuff, you can, as long as you get the lock. So if you get the lock, at some point you're going to release the lock, right? You know that. So you get the lock, you can run this. As long as this block 4 is not related to block 2, you can run that, right? So now you can actually benefit from these parallels. But the interesting part is here. In order to get to block 6, you need to get the lock A, and then you need to also get the lock B. So you can actually request acquiring lock A and B in parallel. Not in parallel, but back to back. You get this lock, and then you get the lock B. And if you get all these locks, then you can actually run block 6. You can see that's actually quite intuitive, but it's actually not very easy to implement. But yeah, this clearly provides very good parallels. Yes.
So are we going to be consistent within the acquired region or outside the?
No, you need to be consistent for that, for acquire. For that, exactly. Yeah, exactly. So you need to be consistent for your synchronization variable, essentially. So order matters for when you are operating on synchronization variables. And you don't have many synchronization variables, hopefully, in your code.
So for section 4, it doesn't matter what the order is.
Exactly. Yeah. So if you want to learn more about weak consistency, you can check these papers. They are actually quite well-written papers with a lot of interesting techniques. Yeah, I think I already also presented this release consistency in the previous slide. So you can check release consistency from this paper as well. So now let's kind of conclude with some trade-off analysis. So of course, with weaker consistency, advantage is that no need to guarantee a very strict order of memory operations, which is really good. And that enables the hardware implementation of performance enhancement techniques to be simpler, like out-of-order execution caches, and can be higher performance than stricter ordering, which is clear. But as a disadvantage, you have more burden on the programmer or software because you need to get the fences and labeling of synchronization operations correct. And debugging is also harder to reason about what went wrong. And that's, yeah, but despite all these issues for the programmer, all this year, people realize that we need to make the programmer life a bit harder in order to provide this consistency model, because sequential consistency is actually just too strict and doesn't really make sense because then it adds a lot of overhead to the architecture. And it's also another example of programmer microarchitecture trade-off that we've seen a lot in this course, in many cases. Question? Okay, so you can check these papers if you are interested. But this topic is actually very interesting for exam. So I'm gonna show some sample exam questions. I'm not gonna solve them. You can solve them or just check the solution for that. But this is, for example, one example question that we had. This is like the two threads here, thread A and B, and they are concurrently running on a dual core processor that implements a sequentially consistent memory model. So that's the assumption. And we say that assume that the value at address basically hex 1000 is initialized to 0. So that's the initialization. And these are the two codes we have. So the first question is that list all possible values that can be stored in register 3, R3, after both threads have finished executing. Like depending on the order of these instructions, like we have interleaving, right? And you know that when we have sequentially consistent model, we might have actually, and we do have actually a lot of interleaving across memory operations. The only thing is that these orders are the same from the perspective of thread A and thread B. So that's the only thing here. But we might have, and we do have a lot of orders. So depending on each order, you might have different values for register 3. So you can practice on it, of course, at home. The next part is that after both threads have finished executing, you find that these values for these registers, how many different instruction interleavings of the two threads produce these results, essentially. This is also not that hard, but it might be a bit like, you need to basically spend some time in solving these questions, of course. What's the total number of all possible instruction interleaving? You need not expand factorials, essentially, here. On a non-sequentially consistent processor, is the total number of all possible instruction interleavings less than or equal to or greater than your answer to question C? This is also interesting to think about. You can easily find the solution actually for all these. There might be actually also some homeworks question. And you can check for solution of them. This is also another example that we provide more, let's say, like detailed code, and then we ask some question about, do you find something that could be wrong in the C code segments? Explain your answer, for example. And then multiple other questions. So this topic is actually quite interesting for exam. Also for architects, of course. But yeah, and that's all. Question? Okay, then we are done with the first part. After, let's have a break. And after that, we can continue with cache coherence. Let's have a 15-minute break. Hey, welcome back. We're gonna continue with cache coherence, which we already actually discussed, like at least the definition. So caching in multiprocessor, you know that it's not only complicates ordering of all operations, as we already discussed, a memory location can be present in multiple caches, and that prevents the effect of a store or load to be seen by other processors. It also complicates ordering of operation on a single memory location, which is the topic of today, this lecture, essentially. So a single memory location can be present in multiple caches, which makes it difficult for processors that have cached the same location to have the correct value of that location in the presence of update to that location. We're gonna see actually with some example. So that's the definition of memory consistency and cache coherence, which we already covered. These are some required reading. This Kohler and Singh book is actually very useful for this topic. And we're gonna also use a lot from this paper, from this book. But yeah, so you can check these recommended papers as well. So this is a shared memory model, essentially, that many parallel programs communicate through shared memory. We also have another paradigm, which is message passing. Like whenever you want to communicate across processor, you send a message. We actually kind of seen it in also one of the lecture, I guess last week. But in shared memory model, essentially you have a part of your memory which is shared, and you use that shared section of the memory in order to communicate, in order to synchronize, communicate, or whatever. So all these things happen in that shared memory. So like processor 0 can write to an address, and that can be followed by processor 1 reading. So this way, processor 0 and processor 1 can communicate information, essentially. So each read should receive the value last written by anyone. And that's the key here, which we're going to see that this can be not true, actually, when we have caches. So this is a basic question that we want to answer here. If multiple processors cache the same block, how do they ensure they all see a consistent state? Let's see with some examples. So processor 2 load X value from the main memory to register 2, and the value assuming the value is 1000. After some time, processor 1 also loads that. Then processor 1 can update that to this value, 2000. After some time, P2 actually wants to load this block again. So since P2 still has this value in his cache, it just reads 1000, right? So P2 should not load 1000, and that's the issue that we're gonna see how we can ensure that you don't load absolute data, essentially. Is this example clear? You can understand the issue, right? Okay. So the first question is that whose responsibility is to provide cache coherence? There might be actually some software solutions. We're going to actually provide a very brief overview of software techniques, and then we're going to dismiss them because we can actually argue that true software implementation is almost impossible. So in the end, you need kind of support from hardware, and people actually come up with more, let's say, hardware-based solutions. Of course, you can think of something between, like software-based and hardware-based, and you combine them. But if you want to have a truly software solution and also at the same time effective, then actually we can argue that it's really almost impossible. It's very hard to say something is impossible, but we can say almost impossible here. So the first question is that if you want to do it as a software, can programmer ensure coherence if cache is invisible to software? So we know that caches are essentially, they are not really visible to software. There are some instructions at the ISA that you can know about caches, but after all, I mean, if you want to make sure that software or programmer can ensure coherence, you need to actually communicate a lot of information, a lot of details about your caches to the programmer layer. So one way to provide coherence is actually doing it at a coarse grain. Like you can have page level coherence, and people have come up with those implementation, but clearly it has a lot of overheads. So you lock the whole page. Once the processor wants to operate on data, so you lock the whole page, meaning that only this processor can access this page. Other processors should wait, essentially. And you are doing this coherence at the page granularity, which clearly has a lot of overhead. If you want to update a block or a word, which has nothing to do with other words or other blocks that other processors are updating, you cannot do that, right? Because your coherence protocol is implemented at the coarse grain, essentially. Another solution, or let's say non-solution, I would say, is that you can make shared logs or data non-cacheable. Clearly, it's not a solution, right? So of course, you can say that I'm not going to cache these. And then, yes, that can provide coherence because you erase the problem to begin with, right? You just say that, okay, I don't have cache. So this is, okay, it might be a solution, but yeah, clearly it's not a solution. A combination of non-cacheable and coarse grain is doable, and people have proposed that. You can also think of fine grain implementation that, like the ISA provides a cache flush instruction. Then you actually need some instruction like flush local, which is flushes or invalidates the cache block containing address A from a processor's local cache. Or you can have flush global A, which invalidates the cache block containing address A from all other processors' caches. And you can also kind of a heavy-handed flush cache X that flush all blocks in cache X. Yes, by adding all these instructions, you might be able to provide coherence, but clearly they are not really effective and efficient. Even if they are effective, then puts a lot of burden on programmer and makes programming life really hard. So now the programmer needs to deal with consistency and coherence and together with many other issues as well. So these things are not really easy to handle. So that's why actually people mostly use hardware-based coherence techniques, or at some point also they combine. Any of you is aware of IBM CellBE processor? Have you played with PlayStation? So IBM CellBE is actually a processor which is used in Sony PlayStation. I have worked actually with IBM CellBE, which is used for PlayStation 3. So in PlayStations, you could actually put it in a kernel mode, and you could install a kernel, and then you can run application. You know, you can just use it for a parallel programming. And we've done that actually. I use that also for some. I programmed a lot with CellBE. I actually taught a course for that when I was in Iran. I was teaching there was a course in multi-core programming, and I was teaching how to program GPUs, CellBE, and also multi-threaded processors. So with CellBE, actually, I love that architecture. Honestly, there are many interesting things about CellBE, which some of them, they are really, I would say, advanced and intuitive. But IBM designers, they wanted to make CellBE quite simple. So they said that, okay, we're not going to support cache coherence at all. And everything should be handled by the programmer. And that's why, in the end, even well-experienced people, well-experienced programmer, they cannot really use CellBE easily. I'm not sure about other editions of CellBE. I haven't followed up. I only work with that CellBE, which is used in PlayStation 3. But it was really kind of headache to program and use that. So even I guess IBM engineers, after that, they also realized that that wasn't a really good idea. So there should be something between, not completely software. If you look also to GPU, you can see that GPU, in the beginning, they were not providing any kind of coherence. Essentially, you have only a shared memory, and in that shared memory, which is inside each core, you can provide some sequential, like synchronization. But in GPU, you say that if you are operating on your global threads, you should not really expect that they are coherent or consistent. And then people actually have tried a lot to implement different coherence technique using using consistency model, essentially. So you can look into that if you're interested to learn more about these topics. But there has been a lot of works in order to use software way in order to reduce the cost for hardware. But in the end, people realize that there should be something between or completely hardware. Relying completely on software, it just doesn't work well. Okay. So in the hardware, you can greatly simplify the software job. And one idea is that you can, for example, invalidate all other copies of block A when a core writes to A, for example. So when a core writes to cache block A, you can invalidate all other copies of block A in other caches. I should also say that here we are talking about block. So that's the granularity of the cache coherence that we're going to talk about today. Like we want to have it like the granularity of blocks. It can be also in granularity of words or bytes, let's say, or bits. But of course, that creates a lot of overhead. But this cache coherence at the level of block can cause also some false dependency, which has been actually seen in many actually software works, like software programming. Like when you map your data across different cores, and these cores or threads are operating on essentially different words. But if these words are shared, they are shared across one block, you might actually think that, like the processor thinks that you have coherence issues, and it tries to handle that and cause a lot of performance overhead for you. Even though these threads are not really operating on the same words, they are operating on different words. So if you have the coherence metric at the coherence protocol at the level of words, you could potentially, fix that problem But then it also comes at the price of huge overhead to the design. So it's always trade-off and good to think about it. And now for that, we think that it's actually a programmer's job in order to map data nicely such that you don't run into false dependency much. So hopefully threads that they are operating on different cache blocks. So when you partition your data, you should not partition a cache block across several threads, essentially. But is that easy? It's not easy because sometimes you don't know how cache blocks are, or how your data is going to map to cache blocks. So that's one thing. Another issue is that also there are some applications that your accesses are not that regular. You might have a lot of random accesses, and you're going to run into some false dependencies at some point. Say it again, sorry.
So if you want to format the data in cache,
Mm-hmm. Yes, that's true. Okay, I provided kind of huge background here, but it's good. I think this kind of perspective is good to communicate such that we can follow the lecture better. Okay, so now let's see a very simple coherence scheme, valid, invalid. We can just name it right now. So essentially caches snoop or observe each other's write and read operations. If a processor writes to a block, all others invalidate the block. This is a kind of simple protocol. I'm going to actually explain it in detail now, because after that, we're going to build up on this protocol. So it's very important that we learn about this protocol nicely. So here we are considering a cache which is write through, meaning that when you update a cache block, you also update the main memory. This is write through. And also you have no write allocate cache, meaning that if you have write miss, so clearly it's a miss, right? So you need to update the memory. You don't read the data from the memory, put it in the cache and then update it. You just update the main memory. So that's why you have this no write allocate, right? You don't allocate writes. Of course, if you have your data, you read your data and you put it in the cache, and then you have a write, so you have write hit. So you just update your cache and also update the memory because it's write true. But if you don't have the data and you encounter write miss, you don't allocate that in your cache. Clear? And there are two types of actions here, actions of the local processor and the cache block, processor read and processor write, and actions that are broadcast on the bus for the block, bus read and bus write. So let's take a look at this very simple protocol, which is actually a correct protocol. You can prove it, that this works. Whether or not it's effective, like performance effective, that's another question. But this is a correct protocol. So we have this FSM, you need to keep for every cache block. And also you need to keep for every processor, essentially. And there are some points from different processor perspective. Let's see. We are like as one processor. You want to read a memory address. If you access cache and you're in invalid state, meaning that you have read miss, right? Because it's invalid. So you send this processor read, and also you send bus read to the whole processor, and then you go to the valid state, right? This actually protocol doesn't really do much when you send bus read, but we have this signal here because we're going to use it for other protocols. So now you're in a valid state, and then at some point you do processor write. So you want to write to that block. As long as you do processor read, let's say first, as long as you do processor read, basically you stay in that valid, right? You don't do anything. But when you do a processor write, you need to send bus write. Still you stay here because you have the cache copy. So it's valid, and you have write hit. So you stay in this state. But at the same time, you also send bus write to the bus. So from another processor perspective, if another processor has the data, like it was in the valid state, and it observed bus write, then it goes to invalid state. because it means that the copy that I have is absolute. So I'm gonna make it invalid such that if the processor, like let's say P2, accesses that cache block, it encounters a miss such that you need to go to the main memory and load it. And we know that the main memory copy is actually up to date because we have write through cache, right? So yeah, these things can work, but the thing is that when you want to implement them, you're gonna get to a lot of also race condition, which you need to, and you're actually gonna exercise with that at some point in lab 6, which is again a bonus lab. But yeah, you're gonna implement messy protocol that we're gonna see today, which is actually quite interesting. Okay, question. Of course, I didn't go into all these. Let's see if any of them. Yeah, here also, if you are in invalid state and you send, you have a processor write. This is actually the point that I mentioned, which is we are in no, when we are, our cache is no write allocate. So if your cache block is invalid and you have a processor write, you send bus write, which is important because there might be other copies that other caches have and they need to go to invalid state. But you also stay in the invalid because you don't allocate writes to your cache, essentially. Question about this protocol? Good. Okay, so I'd like to review very quickly some non-solutions to cache coherence. No hardware-based coherence. That we need to keeping caches coherent is a software's responsibility. This makes microarchitectures life easier, but makes average programmers' life much harder. And then we need to worry about hardware caches to maintain program correctness, which usually as a program, you don't really care about that. You need to care about consistency, but you don't really care about coherence when you work, for example, with multi-programming, multi-threading. Also, there are overheads in ensuring coherence in software that can actually come at the price of other overheads, like page protection, as we discussed, also page-based software coherence and non-cacheable. So these are some techniques that we discussed very briefly, but you can imagine that the overheads of them. Yes. Sorry.
Like this approach, potentially with clusters.
Not necessarily faster, because for example, with this page-based software coherence, clearly you're serializing all the cores if they are. I mean, if you can actually map the data to threads at the page level, like each thread works on a page, and they are not sharing, then yes. But then if you are not sharing, then you don't really have a coherence issue, right? So at some point, if you're operating on a shared data, right? If you want to protect that shared data in a page, like say that, okay, I'm gonna consider that page and protect it, then you are serializing all the operations essentially, right? So, I mean, might be faster in some cases, like for example, in terms of microarchitecture. Sometimes your microarchitecture is simpler, meaning that they can operate on larger frequency or higher frequency, for example, But even that, these techniques will add some, other system level issues that overall your system performance, I don't think actually is gonna be better. But there might be also some cases. Do you have some example in your mind? Yeah, so if your data is not shared, exactly. So but hardware-based coherence control also, they don't need to operate much. If you're like, I mean, there might be some, okay, depending on how sophisticated the technique is, once you update a cache block, you need to send this bus write, for example, with this previous technique, right? You need to send bus write command. And if your data, which is with the cache block that you update, is not shared across them, so other basically other cores will receive these bus write, but they don't do anything because they don't have this cache block to begin with, right? But still you send that request. So that actually is not free. So you send that broadcast information. But you can also come up with a better implementation of this protocol in order to reduce that overhead as well. Okay, and another non-solution can be all caches are shared between all processors. Like now we know that, so the reason that we have this cache coherence is that we have local copies of cache, like we have local L1. And so now these copies might not be seen by other processors. But if you assume that all caches are shared, then yes, I mean, everyone is observing everything. But then, yes, we don't need coherence, but at the same time, this shared cache becomes a bottleneck, of course, which is very easy to understand. And very hard to design a scalable system with low latency cache access this way. Of course, and also for L1, you know, you want a few cycle access to L1, and that clearly that cannot be shared across like hundreds of processors. Question? Okay. So in order to maintain coherence, we need to guarantee that all processors see a consistent value or consistent updates for the same memory location. Writes to location A by processor 0 should be seen by processor 1 eventually. It doesn't need to be communicated at that time, immediately, but eventually needs to be observed. And all writes to A should appear in some order. So coherence needs to provide write propagation. So we need to guarantee that updates will propagate, and write serialization to provide a consistent order seen by all processors for the same memory location. So these are the criteria for coherence technique. And essentially, with any protocol, you need to prove that you're providing these two requirements. And of course, we need a global point of serialization for this write ordering. And we're going to see how we can provide that global ordering. So hardware cache coherence, the basic idea is that a processor or cache broadcasts its writes or updates to a memory location to all other processors. Another cache that has the location either updates or invalidates its local copy. Yes.
So we talk about how every processor when it performs writes or reads communicates with other processors. Can that be used to leverage some form of consistency? Because you're already communicating with them.
So there are some works that they like there are techniques that they simplify coherence using consistency model. So the fact that, as I said for GPU, actually there are many works that people try to provide cache coherence techniques, but there are also many other works that they try to implement coherence technique using consistency model. So this is interesting. Yes. The other way around, no,
Anyway, communicating that.
No, cache coherence is very. I'm not sure. Because the cache coherence is actually only talking about one memory location. It doesn't. So you care about cache coherence when you are talking about one memory location, right? But in consistency, you care about all memory locations. So it's kind of, if you think about it, consistency is kind of superset of that. Right? So using cache coherence to implement consistency, at least I don't know about it. Yeah. The other way around is possible, actually. And people, especially as I said, for GPU, I've read a lot of papers. Okay. So another cache that has the location either updates or invalidates its local copy. This is simple. So let's review our basic protocol that we discussed. How can we safely update replicated data? So one option is that we use a update protocol. So we push an update to all copies. So once you update, you also update, you push this update to all caches that you have in your system, and they should update. Another option is that you just tell them that I update this block and they need to invalidate. They need to invalidate their copy essentially. So on a read, if a local copy is invalid, put out request. If another node has a copy, it returns it. Otherwise, memory does. So this is depends on your way of implementing coherence essentially. So sometimes you can get the up-to-date result from another cache copy because there is also point of serialization. So once you put your request on the bus or you're on a shared fabric, all caches are also observing that. This is actually part of a Snoopy cache. We're gonna also see more. But the other caches are observing that bus. And once they see that, okay, you want this block, and cache, for example, for processor 0 has the most up-to-date, it just puts the data on that, right? But it also would be the case that you just read from memory, or you can actually also only say that I'm not getting copies from other caches to simplify things. I'm just getting data from main memory. And that's why, for example, in that example, we needed this write through, for example, cache, for example, right? On a write request, we read block into cache as before. And then for update protocol, we need to write to block and simultaneously broadcast written data and address to sharers. So this is for update protocol. Other nodes update the data in their caches if block is present, essentially. For invalid protocol, you write to block and simultaneously broadcast invalidation of address to sharers, and other nodes invalidate block if their caches if block is present, essentially. So makes sense, right? Essentially very simple. When you write to a cache block, you either send your updated data to other caches or you just send invalidation command. Okay, which one is better? Like many questions that we have seen so far, it depends. So it depends on write frequency and sharing behavior. Like for update technique, if sharer set is constant and updates are infrequent, we can avoid the cost of invalidate and reoccur a broadcast update pattern. So essentially, you don't need to send, your updates are infrequent, so that's good. Whenever that happens, you just send them, and you don't really impose a lot of overhead. However, if data is rewritten without interfering reads by other cores, that updates would be useless. So if you update, you send your updated value to other cores, and other cores also update without reading. So if you update a cache block, send it to another core, and that core actually before updating read that data, at least it's useful, right? That processor reads it and updates it. But if you update, send the updated value to another core, and that core also updates it. And then another core updates it. So this is kind of useless, right? So that's why this update protocol might not be ideal. And in write-through cache policy, bus can become a bottleneck, of course, because you need to inform memory as well. With invalidates, after invalidation, cores has exclusive access rights, which is important. So once you update, you invalidate, you send invalidation requests for other caches. Now this core has exclusive access to that cache block, meaning that you can silently operate on that data. As long as your access is exclusive, that we're gonna actually see how we can support that, that core can easily just silently update, for example, which is good. And only cores that keep reading after each write retain a copy, which again is important. But if write contention is high, it can lead to ping-ponging, rapid invalidation, and require traffic from different processors. Makes sense, right? So there are two cache coherence methods, essentially. How do we ensure that the proper caches are updated? One way is using a Snoopy bus, which is bus-based. Our bus, shared bus, is single point of serialization for all memory requests. So processors observes other processors' actions using that bus. So when processor like P1 makes a read exclusive request for cache block A on bus, P0 also sees this and invalidates its own copy of A. So they are all they are snooping that bus. They are observing that bus and they are taking actions based on that. Another way is actually using directory, which is single point of serialization per block. So you have a directory, which you're gonna actually also see the example very soon. That in directory, you per each cache block, you store what are the cores or what are the processor that has the data, essentially, that has that cache block. And this can be also implemented, distributed across nodes. And then processors make explicit requests for blocks. So in a Snoopy model, once you send invalidation request, you need to broadcast it. You don't know to who should send it. You just broadcast on the bus, right? And if matters to some of these processors, they will take actions. But in directory base, you know what are the cores that they are sharing that cache block. So you can only send requests to all specific cores or caches, essentially. So directory tracks which caches have each block, and directory coordinates invalidation and updates, of course. So let's see a very brief introduction to directory base. Then we're gonna actually move to Snoopy, and then we're gonna get back to directory again soon. So the directory-based coherence, the idea is that a logically central directory keeps track of where the copies of each cache block reside. Caches consult this directory to ensure coherence. So whenever you have a request, you need to consult with your directory. So an example mechanism can be for each cache block in memory, we store P plus 1. P is the number of processors, and 1 is actually if one processor has that cache block exclusively, essentially. So that 1 is because of exclusive bits. On a read, set the caches bit and arrange the supply of data. And on a write, we need to invalidate all caches that have the block and reset their bits. We can also have this exclusive bit, and when you write to a cache block, you can set the exclusive bit as well. So let's see an example here. So we have 4 processors, and here we have also this exclusive bit. Processor 1 takes a read miss to block A. So directory is completely 0, so no one has the data. So essentially, you just read the data from main memory, and then you need to set this bit in your directory to 1, meaning that P1 has this cache block. Then at some point, P3 takes a read miss. Then you also set the P3 corresponding bit to 1. At some point, P2 takes a write miss. Then you need to invalidate P1 and P3's caches, because you know that these two have the data. So you invalidate them. You send invalidation requests only to P1 and P3. And then you support write requests and set this bit to 1, and also set exclusive bit to 1 here. This is really important that we have this exclusive bit, because it shows that, you know, I have this processor has the data exclusively, and that makes it possible to do some operations silently, essentially. So yeah, and after some time, P3 takes the write miss. Then you just reset, and P3 has the data. You set this and also set the exclusive bit again. After some point, P2 takes a read miss. So you provide your supply from P3. It can be also supply from main memory, depending on the way that you implement your directory mechanism. But essentially now 2 processors have the data, and you reset the exclusive bit, because now 2 processors have the data. Yes?
So the exclusive bit only one.
Yes, and that processor writes to that. If you read, you don't set exclusive bit.
From the left part, only one bit.
Yeah. So this exclusive bit actually here in the concept of this example, it means that you like here, the here example is better. Like P3 updates, and it has the data exclusively, meaning that P2, when it's encounter a read miss, directory knows that P3 has the most up-to-date value of that cache block. So basically, P2 asks P3 to supply that data, essentially. Yes.
The size of this directory has to be every unique cache block in the directory.
Yeah, which is, yes. And there are ways actually to reduce the cost, but in the end, it's actually quite expensive. That's true. But that doesn't mean that a Snoopy base is also easier. Because with a Snoopy base, you need a bus, and bus might be okay. Tomorrow, we're going to actually learn about interconnects. But bus might be okay to connect 8 processor or 16 processor. But once you have hundreds of processors, yeah. But then the question is that, do you need to make 1,000 processor coherent? You may not want that, right? You can also think about clustering your chip and try to be coherent in every clusters. And then when you want to allocate your program to them, you don't allocate to all the clusters. You only allocate to those partitions that they are coherent. So you can, of course, make some things. But if you want to keep 1,000 processor coherent, it's not really easy. So there are, of course, a lot of optimization in directory. So directory is the coordinator for all actions to be performed on a given block by any processor, and it guarantees correctness ordering. And of course, there are many opportunities for optimization. For example, we can enable bypassing the directory and directly communicating between caches. We will see example of this optimization later, actually, when we provide directory techniques a little bit with more details. But now let's get back to Snoopy cache coherence. So the idea here is that all caches snoop all other caches read-write requests and keep the cache block coherent. Each cache block has coherence metadata associated with the tag store of each cache. So in that example, we talk about invalid-valid protocol. So you need to keep that metadata for every cache block, right? So this is, of course, easy to implement if all caches share a common bus. Each cache broadcasts its read and write operation on the bus, and which is good for a small scale multiprocessors. But what if you would like to have a 10,000 node multiprocessor? Clearly, it's not easy. So here is an example of that. You have n processors, and each processor has a cache. You need to keep the metadata for coherence in your tag array, essentially. And this is your shared bus. And these are the operations, essentially. Processor read, processor write, bus read, and bus write. And of course, you can also have this bus read exclusive, meaning that you read from your, this data is read exclusively, essentially. So you can think about some optimization. So this is an example that we have seen, a simple protocol, valid-invalid protocol, which is implemented on top of a Snoopy cache. But now we want to see some extension, how we can make it better, essentially. So what if you want write-back caches? So in this example, we consider that we have write-through, right? What if we want to have write-back caches? So that means we want a modified state, which there should be a state that you say that, okay, the data that I have is dirty, essentially. So that's bring us to this more sophisticated protocol, which we call it MSI, Modified Shared Invalid Protocol. That extend metadata per block to encode 3 states. Modified, meaning that cache line is the only cache copy and is dirty. Shared, meaning that cache line is one of the potentially several cache copies. Pay attention to this potentially. Meaning that potentially this cache block is shared, but it doesn't say that it's for sure shared. And also it's clean. So these are 2 keywords here. When you are in a shared state, your cache line is potentially shared, and also it is clean. Not potentially clean, definitely clean. Because if it's not clean, you need to be in a modified state, essentially. And invalid state, which is cache line, is not present in this cache. So when you have readmes makes a read request on bus and transitions to S. So whenever you have a readmes, you go to the shared. And that's why we are saying that we are potentially shared. We don't know. There might be only one copy. but we don't care in this MSI protocol. We just go to the shared state. Write miss makes a read exclusive request and transitions to modify the state essentially. And when a processor snoops read exclusive from another writer, it must invalidate its own copy, if any. So that's how we implement invalid. Make sense? These topics are overall easy, but also sometimes not that easy to reason. So you need to actually go over them multiple times, think about them to digest them nicely, because after all, you might also, again, confuse all these states. But usually they make sense. It's not very hard to reason about them. Okay, and we have this shared to modified, which we call it as an upgrade, because you're upgrading the privilege essentially. Shared modified that can be made without accessing memory via invalidations essentially. Yes. So you send a read exclusive when you have write miss essentially. So when you have write miss, you want to update, right? You want to update that cache block, but you don't have it because it's a write miss, right? So you need to read it. You need to read it, but you don't do read miss. You don't send bus read, yet read request, because if you send that, it means that you don't want to update it. You just want to go to the shared state. You send read exclusive requests such that other cores that they have this cache block, they understand that, okay, this core is gonna update that. So we all need to invalidate our copy. So that's the way that they can differentiate across. So this is the FSM for this more complicated protocol. These are essentially the main difference here. We have this processor write, and you need to send bus read exclusive. And if you are in the, basically if you are in the shared state, meaning that you have the copy, and then you want to write it, so you go to the modified state, and also you send this bus read exclusive to other cores, just telling them that they all need to invalidate. And also you can move from invalidate again to modified as well. So this is the case that you get write hit. This is the case you get write miss. But both, you go to the modified state and you invalidate other basically cache copies. And other copies, when they receive this bus read exclusive, they all need to go to invalid state essentially. Okay, this is important. Yeah, so if you're also in the shared state, but then you get this bus read exclusive, you need to go to invalid. Essentially, once you get this bus read, when you see this bus read exclusive on the bus, you need to invalidate your copy. So that's why you go to this state of invalid.
Logical reason why bus read exclusive instead of bus, right?
No, this is just, I guess, naming. Yeah, this is a kind of terminology. And if you check different also books and paper, you're gonna see a lot of different terminologies. But the reason about this is that you want to read this. I agree, actually, you want to write it. That's true. But yeah, it is exclusive because your access is gonna be exclusive. You want to update. Question.
Which side is
right? This side. When you are in an invalid state and you want to write to that cache block. So you go from invalid state, you go to modified state. So with processor write. And once you are in the modified state, as long as you see this processor, because you have this copy exclusive, right? So you do this processor read, processor write, you don't need to inform anyone, essentially. And that's the beauty. Yes. Yeah.
Essentially a read, right? Because we have to write also with exclusive and from memory side.
Yeah, that's true actually. Because you need to read it, bring that cache block. Thank you. Okay. But now the question is that can we do better than MSI? So a block is in no cache to begin with. So essentially the problem with MSI is this thing, that when you are in an invalid state and you read, you go to the shared state. So you are just assume that your data is shared, even though it might not be shared, You might have the only copy in the system. So that's the main problem with MSI. So this is what is written here. On a read, the block immediately goes to shared state, although it may be the only copy to be cached. No other processor will cache it. So why is this a problem? Suppose the cache that reads the block wants to write to it at some point. So you need to broadcast essentially, right? While if you have that exclusive copy, you can just silently update, right? It needs a broadcast. If the cache knew it had the only cache copy in the system, it could have written to the block without notifying any other cache, which saves unnecessary broadcast of invalidations. So that's bring us to this solution, messy, modify exclusive shared invalid. But essentially, we add another state, which is exclusive state. And the idea is that this state indicates that this is the only cache copy and it is clean. So when you are in an invalid state and you want to read the data, if you can actually read it exclusively and get to the exclusive. So how you can realize that you have the only copy? One way is to use wired OR implementation. So you have bus and all caches are, they are observing this bus, right? When you are in an invalid state and you want to read a cache block, all caches they are observing the bus, right? If they have the copy of this, they can assert the bus, or they can assert this wired OR. Like this is a wire that if one of them is one, then in the end is one, meaning that your access is not exclusive. But if none of these caches they assert this wired OR, all of them put like 0, let's say, then the result of this wired OR would be 0, meaning that I can get the copy exclusively. And then you move to the exclusive state. And the good thing here is that you can silent transition from exclusive to modified with writes. This messy is also called the Illinois protocol, which actually has been designed by Patel and one of his master's students in 1984. Okay, yeah, you can see here. So you're in an invalid state and you need to read data. You send a processor read, and if only this processor has data, you go to the exclusive clean state. But from invalid, if you send processor read and others also have this data, you go to the shared clean, essentially. Now we have two different states, exclusive clean and shared clean. The good thing is that now you can silently go from exclusive clean to exclusive modified state. Clear? This is another way of looking at messy state machine. It's very similar, so you can also check. This is from Kohler and Singh book. And this is your lab, which we're gonna release at some point, lab 6, that you need to implement messy. Even though the protocol makes sense, you're gonna encounter a lot of issues when you want to implement it and make it work. You're gonna see, which is quite, it's not interesting that you're gonna encounter issues, but it's interesting to see how these things are hard to implement. Like this messy protocol has been used in Pentium Pro, and that actually has some bugs. So later on, people actually, even though they test a lot and the protocol makes sense, the protocol works, right? But once you want to implement it, actually make it work is a hard task. So that's why this lab is actually quite interesting. So I like also to emphasize these two terminology, downgrade and upgrade. So a transition from a single owner state, like exclusive or modified, to shared is called a downgrade because the transition takes away the owner's right to modify the data. And another terminology, upgrade, which is a transition from shared to a single owner state, exclusive or modified. then we upgrade it. So it's just a terminology that you need to be aware because. And this is your lab. This is also in the MESI protocol that has been used in Intel Pentium Pro. But let's see how if we can do better. So now I like to discuss basically some trade-offs. So should a downgrade from modified? Should we go to the shared state or invalid? So shared is that if data is likely, so you are in a modified state, right? And then another core wants to have the data essentially. Are you going to the shared state, meaning that I want to be one of the cores that has this data, or you just invalidate your copy? It depends. So shared, it makes sense if data is likely to be reused before it is written by another processor. And invalid if data is likely to be not reused before it is written by another, essentially. So again, it depends. You can actually think of some intelligent techniques that decide, but those can also complicate things even more. Cache-to-cache transfers. On a bus read, should data come from another cache or memory? Should we supply the data from memory or from another cache? So another cache may be faster if memory is slow or highly contented, but from memory is simpler, no need to wait to see if another cache has the data first, and less contention at other cache. And that requires write back, but this requires write back on modified downgrade. So once you are downgrading from modified state, you need to write back to the memory. And that brings us actually to another model, which is noisy. Write back on modified to shared needed since shared state is clean. So that's the definition of shared state, which is clean. So when you want to go from modified to shared, you need to write back. Can we avoid that? One possibility is we define a state named owner in Moisey protocol that essentially one cache should own the latest data. The thing is that when you, from the modified state, you go to the shared, and all of them, they have updated data. So you actually communicate. But once you want to evict the data, who is responsible to update the memory? So that's the thing, you know, that's the thing that you need to make it clear. So that can happen with this owner attribute. So once you go to the shared state, one processor is responsible for this specific cache block to update the memory as well. So memory write-back happens when all caches evict copies, essentially. So MESI actually has some problems. Again, like the observation, as I said, shared state requires data to be clean. All caches that have the block have the up-to-date copy, and so does the memory. And that problem is that you need to write back. So we can improve it. One idea is that we do not transition from modified to shared on a bus read. We just invalidate the copy and supply the modified block to the requesting processor directly without updating memory. We actually discussed it. So it can be useful in some cases. If your data is not likely to be used, right? You don't have future accesses or read to that data. So it might be it might make sense to just invalidate for that cache block. The second idea is actually transition from modified to shared, but designate one cache as the owner who will write the cache block back when it is evicted. So that's the key here. Now, shared means shared and potentially dirty. So you can actually implement it by adding another state to your state machine, or you can change the definition of your state. Now, the shared state, you can define it as shared and potentially dirty, which can also implement that. And this is a version of Moisey protocol. But essentially, the trade-off in sophisticated cache coherence protocol, the protocol can be optimized with more states and prediction mechanism. So you can reduce unnecessary invalidates and transfers of blocks. However, more states and optimization are more difficult to design and verify. Like it's not only about designing them, it's also like making them work and also verify them. As I said, even for messy that people test it, later on people observe bugs. So it's very hard to make this works. And also we have this, they provide diminution returns, meaning that from valid invalid protocol to MSI, you actually observe huge improvement. From MSI to messy, you observe a little bit less improvement. From messy to noisy, you see some improvement, but not that much. And that's reduce, your improvement and your basically returns is get lower and lower as you optimize more and more. So at some point, it doesn't really make sense. Like it's not worth it, depending on your trade-offs, essentially. Question? Okay, nice. So yeah, this is the two protocol. Now let's compare them very quickly. Like a Snoopy cache miss latency critical is short. Essentially, we need to just request. You need to check this bus transaction to memory. And there is this global serialization, which is easy to implement as long as you have a bus. So bus provides this already. So implementing that global serialization is easy. And it's simple, which can adapt bus-based uniprocessors easily. But it relies on broadcast message to be seen by all caches in same order. Essentially, having this bus is not easy. Bus is not scalable. At some point, you need to design a virtual bus. So you have a network, which is not a bus, but you can make a virtual bus in that network. We're gonna see a little bit actually tomorrow how we can do that. But this is not really easy to implement. With directory, it adds indirection to miss latency, which is, it can cause some critical paths. It can increase the critical paths. So like request goes to directory and then memory. And it requires extra storage space to track share sets. This can be approximate. You can actually reduce that by, because false positives are okay. I mean, at least for correctness. So you can think of storing like some Bloom filters, essentially. So you can have your directory as Bloom filter that since it doesn't, so Bloom filter does not have false negatives, right? So it's okay for correctness. But false positives can essentially impose some performance overhead, which we like to minimize. Protocols and race conditions are more complex for high performance. But the good thing for directory is that it does not require broadcast to all caches and exactly as scalable as interconnect and directory storage. This is much more scalable than bus. So you can easily, you can distribute your directory across a lot of cores. And as long as you can scale your interconnect, hopefully you can also scale directory well. Okay. Let me quickly also revisit directory base, and then we can take 5-minute break. Unless there are questions. Okay. So logically, central directory keeps track of where the copies of each cache block reside, and caches consult this directory to ensure coherence. There can be some example mechanism. This is one example. For each cache block in memory, we store p+1 bits. We already discussed it. And on a read, we set the cache bits and arrange the supply of data. And on a write, invalidates all caches that have the block and reset their bits. We can also have this exclusive bit associated with each block for that. We already seen this example. Yeah, so essentially directory base is required when scaling past the capacity of a single bus. So when we know that this single bus cannot be really scalable, we can, it's really important to use directory base. And it can be also distributed. So coherence still requires single point of serialization for a given block for write serialization, but you can actually distribute it. So serialization location can be different from different blocks. So the point of serialization can be different when you distribute your directory, meaning that the metadata for different cache blocks can be stored in different versions of directory. So then the point of serialization is different for every cache block, but still there is a serialization point of view. So it's very also interesting that we can reason about protocol for a single block, one server, which is directory node, and many clients, which is private caches. So now that you have this intermediate node, you can actually make it intelligent. So that directory can make a lot of decisions, essentially, because you're consulting with another node, like a server, and you can actually implement different algorithms in that server, essentially, right? So that's actually quite interesting. And yeah, another point that I wanted to mention here is that with directory, you can easily also update your protocol. With a Snoopy base, for example, if you want to go from MSI to Messi, you cannot, right? You just need to redesign the whole thing. But with directory, you can actually have some storage that those bits or data shows how you make decision. Or it can actually in the directory can be a software code or something like that. You know, you can just update that, and then the policy can be different. So for directory data structure required to, this data structure is required to support invalidation and cache block request. So the key operation to support is set inclusion test, which as I already discussed, false positives are okay. Want to know which caches may contain a copy of a block, and basically in order to avoid invalidations. But false positive rate, they comes at the price of performance overhead. Most accurate and also most expensive way is to have full bit vector. But of course, that's not happening if we have many processors. So we can also use this compressed representation using linked list, Bloom filters. They are all possible. And people actually have worked on compressing directory a lot as well. I should also say that directory that we have in our hardware is actually a cache for a main directory. Because your main directory might be actually huge, right? So if you cannot keep it on chip. So sometimes people cache directory, but we have inside the hardware. And the main directory is stored in the main memory, essentially. Okay. So basic operation, essentially, they follow semantics of a Snoop-based system. So they are not really that different, but with explicit request and reply messages. So you need to communicate with your directory, which is like a server. You communicate and that reply to you. So directory receives read and read exclusive and upgrade requests from nodes and sends invalidate downgrade message to sharers if needed. And also the directory forwards requests to memory if needed and replies to requested and updates sharing state. Let's see some example, but before that, as I said, protocol design is also flexible because you can actually implement different technique, right? Because it's another node and actually you can reconfigure it as much as you want. I mean, of course, you need to consider some reconfigurability in that directory, but as long as you consider that, you can easily do it. Okay, so yeah, here's one example. Processor 0 wants data, so acquires an address for reading. It accesses home, which is home directory. And then this home directory sends data exclusively to processor 0 or send it in the shared manner. Again, you might have different policies here, and directory can implement different policies. Or for example, directory can ask another node, like processor 1, to acquire the data, send the data to the P0, essentially. So P0 wants to read the data. This home directory knows that, okay, P1 has the data, has the updated data. So we'll ask P1 to send the data to P0, essentially. Read exclusive with the former owner. So processor 0 sends this read exclusive command to home. And then this home directory needs to send invalidate request to the owner. And then owner sends a revision. As I said, there are many different terminologies here. This revision is like revised or update to that cache block, essentially. So this owner sends the revision of that cache block to the home directory and also sends it to the processor 0. And here also another example when you have contention and how you resolve that. So both processor 0 and processor 1, they send read exclusive to the home directory. Home directory acknowledge one of them and send the data to that. And for other one, you can send acknowledge, you can send NAC, or you can, for example, queue the request, like queue the request and acknowledge or service when you have time. And that makes processor 0 happy and processor 1 unhappy. But at some point, processor 1 sends read, repeats its request, read exclusive to the home directory. The home directory sends invalidate to the processor 0 and supplies data to P1. Sounds good, right? And P1 eventually happy. But of course, when you have contention, you have issues. So you need to escape race conditions by NACking requests to busy entries, like pending invalidate. Original requester, they need to retries the request. Or you need to queue request and granting in sequence. And of course, that comes at the fairness issues, like which requester should be preferred in a conflict, interconnect, delivery order, and distance. All these matters. Like if your, as I said, directory is actually distributed across nodes, right? So your processors are in a network and directory is also in the network. Sometimes the cache block that the processor P1, let's say, requests, like P1 and P, let's say 100, they both request cache block X. And cache block X is stored in a directory which is closer to P1, like in the network. So P1 can access that directory in, let's say, 1 or 2 hops, let's say, but P100 needs to take 100 hops to get to that directory. So now, okay, now you have different definition of fairness. This is closer and that one further. So what should we do, essentially? Should we basically NAC processor 1 just because another P100 needs to walk 100 hops to get to that? So there are many basically challenges here. And pinpointing can also, this can be reduced with protocol optimization, of course, or better higher level synchronization. So in the end, there should be effort from both hardware and software to make things nicer. So how large is the directory? These are some scaling questions. How large is the directory? How can we reduce the access latency to the directory? How can we scale the system to thousands of nodes? Can we get the best of snooping and directory protocols with heterogeneity, which you can check this token coherence. It's a very nice paper that's, take advantage of both. And again, this is also a very nice topic for the exam. So you can see some example question here. I'm not gonna review the answer, you can see later. This is also not that new. I think you have seen this paper, Moisey Prime, in our cache coherence, not cache coherence, our RowHammer lectures. So people actually have shown that the coherence protocol in Moisey can actually cause RowHammer. And this paper actually shows that problem and prevents coherence-induced hammering in commodity workloads, which is actually quite interesting. Okay. Let's take a 5 minutes break, and then I will provide, or we can actually continue and then finish early, whatever you prefer. 5 minute break now? Okay, no one votes for that. Okay. So now I want to very quickly talk about the cache coherence in a recent example. Remember that when we have lectures on processing memory, we say that this memory-centric design, in order to make it work, you need to also revisit the entire stack, right? And you need to also address a lot of adoption issues. And we've seen this slide that there are many barriers to adopt PIM. And essentially, coherence is actually one of them. Yes, here. Coherence and synchronization is one of them. So we actually work on that. This work, lazy PIM, and also the extension of that, which a lot of improvements, Conda, is actually the work that provides cache coherence support when we have near data accelerators, or let's say processing near memory engines. I'm gonna cover this paper very, very quickly. I'm not going into details of that. Hopefully you will read it as part of your readings, but I will give you the high level idea. So essentially, you know that we have specialized accelerators, and the NDAs, this NDA here is the near data accelerator. So now the challenge is that you have NDA compute unit in DRAM, and you have your CPU, which level of caches. So now the challenge is that how you make coherence between NDAs and CPUs. So these two should be coherent, essentially, right? Because after you can also think of NDA as another core, right? So now there are different cores, but some of them, they are not the cores at the CPU. So, but now you still need to make them coherent. So NDA applications generate a large amount of off-chip data movement if you want to make it coherent. And it's impractical to use traditional coherence protocols. I'm going to show some results for that. We extensively study existing NDA coherence mechanisms and make 3 key observations. These mechanisms eliminate significant portions of NDA's benefits, meaning that you use this processing near memory to improve energy and performance, but once you want to make it coherent, and if you don't support coherence intelligently, then you're gonna, basically you don't get performance improvement. At some point, you actually can reduce performance, and also worsen energy consumption. So the majority of off-chip coherence traffic generated by these mechanisms is unnecessary. That's actually one of the key observations. So which is good. You don't need to send a lot of coherence traffic if you do it intelligently. And much of the off-chip traffic can be eliminated if the coherence mechanism has insight into the memory accesses. So we use an optimistic approach, which I guess you are aware of this terminology, that you're optimistic. You say that everything should be okay. So I assume that things should be okay. So you run NDA and assume that everything would be fine, meaning that you're not gonna into coherence issues. But then after that, you need to check. After the execution, you do these coherence checks. And we need to perform only the necessary coherence request, meaning that we need to update or rerun execution. Okay, so let me provide some more background. So NDP, you know, I'm not going to talk about it. So these are the applications that we look into. For example, here in different domains, hybrid databases and graph processing. So we find not all portions of applications benefit from NDA, meaning that these applications have memory intensive and compute intensive or cache friendly portions, meaning that you need to use both NDA or processing near memory engines and also your CPU at the same time, right? Because you don't offload the whole application to either of these engines, essentially. So the first key observation is that CPU threads often concurrently access the same region of data that NDA kernels access, which leads to significant data sharing, which is not good news, essentially, meaning that it's important to make them coherent. But the second observation makes things interesting, like CPU threads and NDA kernels typically do not concurrently access the same cache lines, which is good. And then we are actually benefit from this second key observations. So this is also the report from this graph application, connected components. So we conduct some analysis on existing coherence mechanisms. We analyze 3 existing coherence mechanisms. One is non-cacheable. Like we mark the NDA data as non-cacheable, essentially, meaning that the CPU needs to access main memory for any of the, when it needs to operate on these cache blocks or memory addresses. Another one is coarse-grained coherence. We get the coherence permission for the entire NDA region. So NDA get the coherence permission, and then CPU should not do anything. Basically, if CPU needs to access that region, it needs to be installed. And another one is fine-grained coherence, which we implement traditional coherence protocols, like MESI, these protocols that we already discussed. You can check the paper for details of that. But essentially, you can implement that, right? You need to send all these read requests, write requests. I mean, everything needs to communicate through the bus, right? Clear? So with non-cacheable, you mark NDA data as non-cacheable. So CPU generates a large number of off-chip accesses, and this significantly hurts CPU trace performance. We observed that non-cacheable fails to provide any energy saving and perform actually 6% worse than CPU only. So even though you have processing near memory engine, overall with this non-cacheable approach, your performance is 6% worse. With coarse grain, basically unnecessarily flushes a large amount of dirty data, especially in pointer chasing application. So you need to get permission, right? When you want to access that region. So we use a coarse grain logs to provide exclusive access, like CPU is running, and then NDA wants to operate. So we access to NDA data, and then CPU stop because it doesn't get the permission, right? And once NDA is, so let me explain again. So CPU is running, is doing some computation, NDA is also doing. So they are overlap at some point, but at some point CPU reaches to the region that NDA is operating on. So CPU requests to access that region, and NDA of course doesn't permit that because we are using this coarse grain block management. Coarse grain locks. So then as a result, the CPU needs to be stopped. And the CPU can continue when NDA is done. So that's the way of implementing these coarse grain locks, essentially. So we observed that, yes.
So this must be included in the post code.
Oh, yes, yes, yes.
And we use virtual address.
Yeah, it needs to be in the host core, but also it needs hardware support as well, right? Both, yes.
And we operate at the virtual address.
Yeah, of course. Yes, virtual address, yeah. So this coarse grain fails to provide any performance benefit of NDA and performs actually 0.4% worse than CPU only. Again, another way is fine-grained coherence. Using fine-grained coherence has two benefits: simplify NDA programming model and allows us to get permission for only the pieces of data that are actually accessed. But the problem is that we have basically there are a lot of off-chip coherence traffic through this bus, and that causes a lot of issues. So we observed that fine-grained coherence eliminates. So fine-grained coherence actually provides some performance improvement compared to other coherence techniques, but it eliminates almost 72% of the energy benefits of an ideal NDA mechanism. An ideal NDA mechanism meaning that you don't really do any coherence. You ideally assume that you don't need to do any coherence checks. And here are the results that you can see. This is the ideal one, that shows the room for improvement. And see, everything is also normalized to CPU only, meaning that you don't have NDA access, processing near memory engines. So non-cacheable, you can see that it reduces performance. Coarse grain, in many cases, actually reduces. In some cases, slightly outperform. Fine grain actually provides some performance improvement. But in terms of energy, you can see that fine grain actually reduces. Also reduces energy, but like you can see a huge gap between ideal NDA and these fine grain methods. Yeah, you can walk through all these animations. So that's the motivation of this work. Like poor handling of coherence eliminates much of NDA's benefits, and the majority of off-chip coherence traffic is unnecessarily. Our goal is to design a coherence mechanism that retains benefits of ideal NDA and enforces coherence with only the necessary data movement. That brings us to Conda. I will just provide the overall key idea of this technique. So we leverage two key observations. We know that having insight enables us to eliminate much of unnecessary coherence traffic and a low rate of collision for CPU threads and NDA kernels from the observation that we had. So we propose to use optimistic execution for NDA. So NDA executes the kernel, assumes it has coherence permissions, and then gains insight into memory accesses. When execution is done, performs only the necessary coherence request. That's the whole technique, but the way that we implement it is like that. So CPU thread is executing. At some point, we start the optimistic execution for NDA, so we offload the kernel to NDA. And this is optimistic. We don't check any coherence technique. And you can see that concurrent execution between CPU and NDA can happen. There is no coherence request while we are doing computation. And then after that, we need to resolve coherence. We need to see if things are okay or not. So basically, we need to commit or re-execute, essentially. So how we do that? We just check the signature. So essentially, once NDA is running, you get the signature, meaning that what are the basically memory accesses that you touch. You know, you can have the record of them using. You can actually summarize them with a hash function, essentially. But yeah, that signature is actually kind of make a signature of all the memory accesses that you touch, or essentially memory exactly you touch. And also the memory request that you also touch in CPU. And then you need to compare NDA sends signature to CPU, and then you need to compare these signatures. And based on that, you can decide to commit or re-execute. So how do we identify coherence violation? So coherence requests are only necessary if both NDA and CPU access a cache line, and at least one of them updates it, right? Clear. So in the paper, you can actually read, but we discussed 3 possible interleaving of accesses to the same cache line. So NDA read and CPU write. So this is coherence violation, essentially. That NDA read on a block, that CPU writes to that block. So this is coherence violation. But another way, NDA write and CPU read, and NDA write and CPU write. From the point of view of NDA, these are not coherence issue because NDA does not read something which is wrong. But then you might have consistency issue, which kind of assume here. I mean, you can actually check the paper for more detail, but these things, these 2 things can be handled by consistency model, essentially, because kind of ordering that you have. So here is an example. CPU writes to this cache block, and NDA reads to this cache block. So now we have coherence issue because NDA reads old value of Z. And we need to ask CPU to flush Z to the DRAM and then re-execute NDA, essentially. But here we have write and read to Y, and here also in NDA we have write to Y. So this is not a coherence issue because C4 and C5 are ordered before N5. So you can handle that with your consistency model, essentially. Okay, so now we have a bunch of slides about architectural support that I'm gonna just skip. You can check for detail of the mechanism. But yeah, the important thing here is that this L1 cache that you consider for your NDA core, you cache things, but you don't commit things. So you commit them to the main memory once you make sure that what you have executed is correct. So after checking like the signature, if things are okay, you just commit things. A lot of slides, you can see. Okay, and here are also some results. Like that's basically Conda. You can see that it bridges the gap nicely, and it reaches to the kind of almost the performance of ideal NDA. So NDA only, sorry, let me, yeah. Conda consistently retains most of ideal NDA benefits and coming within 10% of the ideal NDA performance, which is good. And you can also see the good results for energy consumption. There are many other results in the paper that you can also check. And also the conclusion that I'm not going to repeat it. Okay. So yeah, if you want to learn more about details of this technique, because I just provide the overall idea of this technique, please check the paper. It's also going to be one of your reading, of course. And that brings me to the end of this lecture. Any question? Okay, so tomorrow, there are actually some other topics in cache coherence that Professor Mutlu actually will discuss them next week on Thursday, I guess. But tomorrow I'm gonna talk about interconnects, which you kind of know why interconnect is actually very important. We discuss a lot about interconnect in today's lecture in cache coherence. We're gonna learn a lot about interconnects, which is interesting. So see you all tomorrow, and have a nice evening.